Hello there and welcome to the Sleepy Science channel. Tonight we'll be exploring one of humanity's oldest companions, fire. A force of transformation, warmth, and light that has shaped our world since the very beginning. Fire dances in hearths and campfires, glows in candles and lanterns, and burns within the hearts of stars themselves. It is both familiar and mysterious, comforting yet powerful, ancient yet ever-present. From the smallest flickering flame to the roaring infernos that reshape landscapes, fire has been our guide through darkness, our tool for survival, and our gateway to civilization. If you enjoy these quiet explorations, I invite you to like and subscribe or share a simple thought down in the comments. It helps others find their way here too, one sleepy soul at a time. But for now, all you need to do is rest, settle in, and allow the warmth of these gentle stories to carry you into peaceful sleep. Let's begin. Fire is a chemical reaction, not a substance itself. When we look at a flame, we might think we're seeing a thing, an object we can point to. But fire is not matter in the traditional sense. It is a process, a chemical reaction happening before our eyes. When fuel combines with oxygen and reaches the right temperature, combustion begins. Molecules break apart and recombine, releasing energy as heat and light. What we perceive as flame is actually glowing gases, heated to the point where they emit visible light. The colors we see, the dancing movements, the crackling sounds, all of these are manifestations of chemistry in action. Fire exists only as long as the reaction continues, sustained by fuel, oxygen, and heat. Remove any one of these elements, and the flame extinguishes, returning to stillness. The flames we see are actually glowing carbon particles and gases. Within every flame, tiny stories unfold at the molecular level. As wood or other organic materials burn, they release carbon particles so small they float in the hot gases. Rising from the fire, these particles heat to extreme temperatures, glowing white, yellow, or orange, depending on how hot they become. The familiar warm colors of a candle flame or campfire come from these incandescent carbon particles, each one a microscopic ember catching light. The blue at the base of a flame appears, where gases burn most completely, where temperatures soar highest, and combustion is most efficient. In that blue zone, carbon monoxide transforms into carbon dioxide, releasing energy in a cascade of molecular transformations. Every flicker, every shift in color, represents countless particles dancing through chemical change. Humans have controlled fire for at least 400,000 years. Long before written language, before agriculture, before the wheel, our ancestors learned to command fire. Archaeological evidence suggests that early humans began controlling fire, perhaps 400,000 years ago, though some researchers believe fire use extends even further back. This mastery changed everything. Fire provided warmth against the cold, light against the darkness, and protection from predators that feared the flames. It allowed early humans to cook food, making nutrients more accessible and expanding the variety of edible plants and meats. Around ancient fires, communities gathered, sharing food and stories, strengthening social bonds. Fire became the center of human life, a focal point around which culture itself could form. To imagine those first controlled flames is to glimpse a pivotal moment in our story when we transformed from creatures living in nature to beings who could shape it. The earliest hearths tell stories of gathering and community. Archaeologists, excavating ancient sites, find charred earth, arranged stones, and ash deposits marking where fires once burned. These hearths, some hundreds of thousands of years old, reveal patterns of human behavior. They were placed deliberately, often in cave mouths or sheltered areas, positioned to maximize warmth and minimize smoke. Around these fires, evidence suggests families gathered, preparing meals, crafting tools, and simply being together. The hearth became humanity's first architecture, a defined space of safety and light in an uncertain world. In the flickering glow, stories were shared. Knowledge passed from generation to generation. Fire made nighttime a social time, extending the day and allowing culture to flourish. Every modern fireplace, every campfire circle echoes these ancient gatherings, connecting us to ancestors who first learned to keep the darkness at bay. Fire allowed humans to cook food, transforming nutrition and evolution. Raw food sustained early humans, but cooked food changed everything. Heat breaks down tough plant fibers and denatures proteins, making food easier to chew and digest. Cooking kills harmful bacteria and parasites, reducing disease. It unlocks nutrients that would otherwise pass through the body unused, effectively making more energy available from the same amount of food. Some anthropologists believe cooking was so significant that it influenced human evolution itself. With more nutrition from less effort, early humans could support larger brains, which require enormous energy. Cooking may have freed time from constant foraging, allowing for tool-making, social interaction, and the development of complex thought. The controlled use of fire in food preparation was not merely a convenience but a revolutionary development that helped make us who we are. Every meal prepared over flame connects us to that ancient transformation. Warmth from fire made survival possible in cold climates. As humans spread from Africa into colder regions, fire became essential for survival. Without it, the northern winters would have been insurmountable barriers. Fire provided warmth that allowed early humans to endure freezing temperatures, to settle in caves during ice ages, to venture into territories no primate had ever inhabited. The ability to create and maintain fire meant the difference between life and death. Communities learned to bank fires overnight, keeping coals alive to restart flames in the morning. They carried fire with them on migrations, transporting embers in careful containers, treating flame as precious cargo. Fire extended human habitat across the planet, from Arctic tundra to high mountain valleys. It was our portable sun, a sphere of warmth and light we could create wherever we went. In the coldest nights, fire meant hope, survival, and the promise of morning. Flames dance because of rising hot air and turbulent flow. Watch any fire and you'll see flames that never stay still. They flicker, sway, reach upward, and curl back on themselves in endless variation. This dance happens because fire creates heat, and heat causes air to rise. As the hot gases from combustion ascend, cooler air rushes in from the sides to replace them, creating a constant flow. This airflow is turbulent, full of swirls and eddies, and the flame responds to every shift in the current. The dance of flame is visible turbulence, fluid dynamics playing out in glowing gases. External breezes add to the complexity, pushing flames in new directions, making them bend and wave. Even a candle flame in a still room dances slightly, responding to the tiniest air currents created by its own heat. The movement we find so mesmerizing is simply physics, but it feels like life itself, breathing and moving with restless energy. Candle flames are teardrop-shaped because of gravity and airflow. On Earth, a candle flame takes on a distinctive shape, narrow at the base, wider in the middle, tapering to a point at the top. This teardrop form results from the interplay between combustion and gravity. The hot gases want to rise, pulled upward by buoyancy, while the wax vaporizes at the base, creating a steady fuel supply. The shape optimizes the flow of oxygen to the fuel, allowing efficient burning. But something remarkable happens in the absence of gravity. In the International Space Station, Astronauts have lit candles and watched flames become perfect spheres, glowing orbs, without a preferred direction, for up. Without gravity to pull hot gases upward, the flame radiates heat equally in all directions, forming a ball. This shows us how much of fire's familiar behavior comes from the environment it burns in. Even something as simple as a flame's shape depends on forces we rarely think about. Different materials burn in different colors, creating the palette of flame. Not all fires look the same. The color of a flame depends on what is burning and how hot the fire becomes. Wood fires glow yellow and orange from glowing carbon particles. Natural gas burns blue because it combusts cleanly and reaches higher temperatures. Copper compounds produce green flames, while strontium burns red, and sodium creates the brilliant yellow of street lamps. Potassium glows violet, and barium burns green-white. This chemistry of color makes fireworks possible. Each brilliant burst carefully engineered by mixing compounds that burn in specific hues. The rainbow of flame tells us about temperature and chemistry, turning fire into a diagnostic tool. Glassblowers and metalworkers have long read the color of their fires to judge heat, knowing that color correlates with temperature. A flame's hue is not merely beautiful but informative, a visible spectrum of the energy being released. The blue part of a flame is actually hotter than the yellow. Counterintuitively, the bright yellow flames that look so intense are cooler than the blue flames at their base. Blue indicates more complete combustion and higher temperatures, often exceeding 1,400 degrees Celsius. Yellow and orange flames, while visually dramatic, occur where temperatures drop and carbon particles glow rather than burn completely. This temperature gradient exists in every candle flame, every campfire, a rainbow of heat arranged by physics. The coolest part of a candle flame, the dark space just above the wick, barely reaches combustion temperature. Move upward through yellow and orange zones of increasing heat, then down to the base where blue flames burn hottest. This invisible architecture of temperature shapes every fire, determining how it burns and what it consumes. To understand flame is to appreciate these hidden layers, the structures of heat that organize what seems like chaos. Oxygen feeds fire by accepting electrons released during combustion. Fire needs oxygen, but why? The answer lies in chemistry's fundamental processes. Combustion is oxidation, a reaction where fuel molecules break apart and oxygen atoms bond with the released carbon and hydrogen. This bonding releases energy, the heat and light we perceive as fire. Oxygen is particularly good at accepting electrons, making it an efficient partner in combustion. Without oxygen, or with very little of it, combustion slows or stops entirely. That's why smothering a fire with a blanket works. It excludes oxygen, breaking one leg of fire's essential triangle of fuel, heat, and oxygen. In oxygen-rich environments, fires burn faster, hotter, and more intensely. Some spacecraft use pure oxygen atmospheres, a dangerous choice as the Apollo 1 tragedy demonstrated. Fire's relationship with oxygen is intimate and essential, a chemical partnership that powers everything from candles to combustion engines. Fire needs three things: fuel, heat, and oxygen, forming the fire triangle. Fire instructors teach the fire triangle as a fundamental concept: fuel, oxygen, and heat. Remove any one, and fire cannot exist. Fuel provides the material to burn, whether wood, gas, paper, or any combustible substance. Oxygen enables the chemical reaction. Heat brings everything to the ignition temperature where combustion begins. Once started, fire generates its own heat, sustaining the reaction in a self-feeding cycle. Fire suppression works by attacking one or more Sides of this triangle: water cools, removing heat. Fire extinguishers smother, excluding oxygen. Fire breaks eliminate fuel. Understanding this triangle transforms fire from mysterious force to understandable process. It's a simple model that explains both how fires start and how they end. For our ancestors, learning this implicitly through experience was crucial for survival. For us, it remains essential knowledge, the basis for everything from lighting a campfire to fighting wildfires. Some fires can burn without oxygen, using chemical oxidizers instead. While most fires we encounter need atmospheric oxygen, some burn with internal oxidizers. Certain chemicals contain oxygen within their molecular structure, allowing them to burn even in airless environments. Gunpowder combines sulfur, charcoal, and potassium nitrate, which provides oxygen for the reaction. It can burn underwater or in the vacuum of space. Some metals, like magnesium, burn so hot they can extract oxygen from water itself, continuing to burn even when submerged. These chemical fires behave differently than ordinary flames, often burning faster and hotter, sometimes explosively. They remind us that combustion is fundamentally about chemistry, not just mixing fuel with air. In oxygen-starved environments, these reactions still release energy, still produce heat and light, still transform matter from one form to another. Fire's versatility extends beyond what we normally encounter, into realms where chemistry provides everything needed for the ancient dance of combustion. Forest fires can regenerate ecosystems and promote new growth. Fire often seems purely destructive, but in many ecosystems, it plays a vital regenerative role. Some forests evolved with fire as a regular presence, developing strategies to not just survive but thrive after burning. Certain pine species have cones that only open and release seeds when exposed to fire's heat. Native grasses in prairies store energy underground, quickly resprouting after fires clear dead material. Fire returns nutrients from dead plants to the soil, clears space for new growth, and resets successional processes. Indigenous peoples around the world practiced controlled burning for thousands of years, understanding fire as a tool for landscape management. Suppressing all fires, as became policy in many regions, actually increased the risk of catastrophic burns by allowing fuel to accumulate unnaturally. Ecosystem fire management now recognizes that some landscapes need periodic burning to remain healthy. Fire destroys, yes, but it also clears, renews, and makes space for life to return, transformed. Lightning strikes spark thousands of wildfires each year. Before humans controlled fire, nature had its own fire starters. Lightning, the discharge of electrical potential between clouds and ground, carries enough energy to ignite dry vegetation instantly. Every year, tens of thousands of wildfires begin from lightning strikes, particularly in remote areas during dry seasons. A single storm system can spark dozens of fires across a landscape. Some ignite immediately in visible flames, others smolder in dead trees or underground in root systems, only to emerge days later. Our ancestors must have witnessed lightning fires regularly, perhaps learning to use naturally occurring fire before discovering how to create it themselves. Even today, with sophisticated fire detection systems, lightning-caused fires surprise us with their timing and locations. They remind us that fire is deeply natural, a regular phenomenon in many ecosystems, as much a part of nature as rain or wind. The spark from the sky has been starting fires long before humanity existed and will continue long after. Some trees have bark thick enough to survive repeated fires. In fire-adapted ecosystems, trees have evolved remarkable defenses. Species like the giant sequoia, ponderosa pine, and cork oak grow bark that can be several inches thick, insulating the vital cambium layer beneath from fire's heat. This armor allows mature trees to survive fires that would kill less adapted species. After a fire passes, these survivors stand blackened but alive, ready to take advantage of the cleared understory and reduced competition. Some even depend on fire's presence. Giant sequoias, for example, grow best after fires, clear the forest floor and open gaps in the canopy. Their thick bark protects them, while fire eliminates competitors. Walking through a forest of fire-scarred but living trees is humbling, a reminder of life's resilience and adaptation. These ancient strategies, evolved over millions of years, show that life and fire have coexisted far longer than humans have been here to witness it. The hottest part of a wood fire can exceed 1,100 degrees Celsius. A campfire's warmth feels gentle, but the temperatures within flame reach extremes. The heart of a well-burning wood fire easily exceeds 1,100 degrees Celsius, hot enough to melt aluminum, to glow white-hot, to transform almost any organic material into ash and gas. The coals beneath active flames burn at slightly lower temperatures but hold heat longer, radiating warmth steadily. This incredible temperature generation from simple burning wood astonished early humans, who found in fire a source of heat far exceeding anything else in their experience. Fire's heat enables metalworking, pottery, glass-making, all the technologies that build civilization. Yet we rarely think about these temperatures when we sit beside a friendly flame, comfortable in its warmth. The fire contains within it extremes we cannot touch, cannot approach closely, yet it shares its warmth generously at a distance. This gift of heat, precisely controlled by distance, made human advancement possible. Smoke rises because hot air is less dense than cool air. Smoke from fire always rises, drawn upward in familiar columns and plumes. This happens because combustion heats air, causing its molecules to move faster and spread out. Hot air becomes less dense than the cooler air surrounding it, and buoyancy lifts it upward, just as a balloon filled with hot air rises. The smoke particles, tiny bits of unburned fuel, and other materials get carried along with this rising air. This natural draft helps fire burn by constantly pulling fresh oxygen in from the sides, while removing combustion products upward. Chimney design takes advantage of this principle, using tall structures to enhance the draft, pulling smoke up and out. On still days, smoke rises straight up in vertical columns. When wind blows, it bends and disperses the smoke, spreading it horizontally. This predictable behavior allowed ancient peoples to use smoke for signaling, creating communication systems visible for miles. The rising smoke was a message written in the sky, telling of fire below. Different types of wood produce different qualities of fire and smoke. Not all firewood is equal. Dense hardwoods like oak, hickory, and maple burn long and hot, making them ideal for heating and cooking. They produce substantial coals that radiate heat steadily. Softwoods like pine and spruce ignite easily and burn fast, perfect for kindling but less ideal for sustained fires. Resinous woods create more smoke and can spark and pop, sending tiny embers flying. Green wood, recently cut and still containing moisture, burns poorly, producing excessive smoke and little heat as energy goes into evaporating water. Seasoned wood, dried for months or years, burns cleanly and efficiently. Different woods also smell different when burning. Cedar produces a distinct fragrance. Fruit woods offer sweet aromas, and mesquite creates the smoky scent beloved in barbecue. Our ancestors learned these distinctions through experience, becoming experts in wood selection. They knew which trees provided the best coals for cooking, which started easiest, which burned longest through cold nights. This knowledge, accumulated over generations, represents deep understanding of fire's partnership with plants. Charcoal burns hotter and cleaner than wood because of its purity. When wood burns in limited oxygen, a process called pyrolysis occurs. The volatile gases and moisture are driven off, leaving behind nearly pure carbon charcoal. This material burns at higher temperatures than wood and produces less smoke because impurities have already been removed. Charcoal making became an essential craft in many cultures, with charcoal burners carefully tending covered piles or kilns, where wood transformed over days of controlled burning. The resulting product fueled metalworking, enabled forge temperatures high enough to shape iron and steel, and powered the Industrial Revolution before coal mining became widespread. Charcoal still serves in cooking, prized for its clean, hot burn and the flavor it imparts to food. The transformation of wood into charcoal is alchemy of a sort, taking a natural material and refining it through fire into something more potent, more specialized, more useful for specific purposes. It shows fire's power not just to destroy but to transform, to refine, to improve. Fire produces light through incandescence and excited electrons. Why does fire glow? Two main processes create light from flame. Incandescence occurs when particles become so hot they emit visible light. The carbon particles in a candle flame or campfire heat to extreme temperatures and glow, producing the warm yellow-orange light we associate with fire. This is the same principle behind old incandescent light bulbs, where a tungsten filament heats until it glows. The second process involves electrons in gas molecules absorbing energy from combustion, jumping to higher energy states, then falling back down and releasing that energy as photons. This creates specific colors based on what's burning. Blue flames show this electronic emission from excited carbon monoxide. Fireworks use both principles, incandescent particles, and electronic transitions to paint the sky. Fire's light has illuminated human existence from our earliest days, pushing back darkness, making nighttime safe and productive. Before electric light, fire was the only significant source of illumination, the sole way to extend day into night. Flames in low gravity behave very differently than on Earth. Gravity shapes fire's behavior in ways we never notice until it's gone. In microgravity environments, flames don't produce the familiar upward-reaching teardrops we know. Instead, they form spheres, burning in all directions equally. Without gravity driving hot gases upward, there's no strong convection current, and flames can actually suffocate themselves if air isn't circulated by other means. This makes fire extremely dangerous. In spacecraft, flames can spread in unpredictable ways, and smoke doesn't rise away, but rather accumulates. NASA and other space agencies conduct combustion experiments in microgravity to understand these behaviors, both for safety and for insights into fundamental combustion processes. Watching footage of spherical flames drifting in space stations is mesmerizing, showing us how much we take gravity for granted. Fire, so familiar on Earth, becomes alien and strange when one fundamental force changes. It reminds us that our everyday experience of fire is shaped by the specific conditions of our planet. The sound of crackling fire comes from moisture and expanding gases. A fire's voice is as distinctive as its light, a symphony of pops, crackles, and roars. Wood crackles when pockets of moisture inside rapidly heat and expand, creating steam that bursts through the wood structure with sharp reports. Resin pockets in pine and other conifers pop similarly, releasing trapped gases explosively. The steady roar of a large fire comes from turbulent airflow, hot gases rushing upward through fuel. creating sustained noise much like wind through trees or water. Over rocks, different materials burn with different sounds. Paper burns with a gentle rustling. Plastic can hiss and gurgle. Metal, when heated sufficiently, can creak and ping as it expands. These sounds are deeply comforting to humans, perhaps coded into us from countless generations gathered around fires. Recordings of crackling fires help people relax and sleep, suggesting our species carries an ancient association between fire's sounds and safety, warmth, and home. Spontaneous combustion can occur when organic material heats itself. Sometimes fire starts without a spark, without flame, without any obvious ignition source. This is spontaneous combustion, and it happens when certain materials generate their own heat through chemical processes. Piles of hay, compost heaps, coal stores, even oil-soaked rags can self-heat. Bacterial action in hay or compost generates warmth. If the pile is large enough, heat accumulates faster than it can dissipate. Temperatures rise, and eventually, the material reaches its ignition point. Linseed oil and other drying oils oxidize exothermically, meaning the chemical reaction produces heat. A rag soaked in linseed oil, crumpled and left in an enclosed space, can heat itself to combustion. Stories of barns mysteriously catching fire often trace back to spontaneous ignition of improperly stored hay. This phenomenon seems almost magical, but follows predictable chemistry. It teaches a crucial lesson. Fire doesn't always need an external spark. Given the right conditions, materials can kindle themselves through accumulated energy, turning potential into flame. Coal seam fires can burn underground for decades or even centuries. Beneath the surface, in places where coal deposits lie exposed to oxygen, fires can ignite and burn for extraordinary periods. Some coal seam fires have burned for hundreds of years, creating hellish landscapes where smoke seeps from ground cracks, where the earth itself grows hot to the touch. The town of Centralia, Pennsylvania, was abandoned because of an underground coal fire that started in 1962 and continues burning today. Lightning, surface fires, or human activity can ignite these seams, and once started, they're nearly impossible to extinguish. The coal provides massive fuel reserves, and the underground environment protects the fire from rain and other surface conditions. These fires consume coal that might otherwise be mined, release greenhouse gases, and create dangerous ground conditions. Yet they also remind us of fire's power and persistence. Once unleashed in the right conditions, fire can outlast generations, burning in hidden chambers, slowly consuming the ancient energy stored in prehistoric forests, now transformed to coal. Peat fires smolder intensely, creating vast underground networks of embers. Peat, the accumulated partially decayed plant matter in bogs and wetlands, represents enormous stores of carbon. When peat catches fire, it typically doesn't flame dramatically. Instead, it smolders, burning slowly with intense heat, but little visible flame. These smoldering fires can spread underground through peat layers, moving silently beneath the surface. Firefighters battle peat fires by the vast amount of water needed to extinguish them. Peat must be thoroughly saturated to stop smoldering. Indonesia and other tropical regions with extensive peatlands experience massive fires during dry seasons, with smoke affecting millions of people across multiple countries. The fires can re-emerge after seeming extinguished, having burned through underground peat layers to new locations. This smoldering combustion is highly inefficient, producing more smoke and carbon monoxide than flaming fires. It teaches us that fire isn't always about visible flames. Sometimes the most dangerous and persistent fires are the ones that glow unseen, quietly consuming fuel in slow, patient destruction. Firefighters use controlled burns to prevent larger, catastrophic fires. The best way to fight fire is sometimes with fire itself. Controlled or prescribed burns involve deliberately setting fires under carefully managed conditions to reduce accumulated fuel. By burning underbrush, dead vegetation, and small trees during cool, moist conditions, land managers reduce the material available for future fires. This mimics natural fire cycles that many ecosystems evolved with and need for health. Native American tribes practiced cultural burning for millennia, understanding that periodic small fires prevented devastating large fires while also promoting growth of desired plants. Modern fire management increasingly recognizes this wisdom. A prescribed burn moves slowly, stays low, and can be controlled by the teams managing it. Without this management, fuel accumulates year after year until an ignition source, lightning, accident, arson, creates conditions for megafires that burn with such intensity they sterilize soil, kill even fire-adapted trees, and can create their own weather patterns. Fighting fire with fire isn't contradiction. It's collaboration with natural processes, using small, controlled burns to prevent catastrophic, uncontrolled ones. Fire tornadoes, or fire whirls, form when extreme heat creates rotating columns. In intense fires, especially wildfires, conditions sometimes create one of nature's most dramatic phenomena: fire tornadoes. These aren't true tornadoes formed by weather systems, but rather rotating columns of air and flame generated by the fire itself. Extreme heat creates powerful updrafts, and if winds are right, these updrafts can begin rotating, drawing in oxygen and fuel, intensifying into spinning vortexes of fire. Some fire whirls reach hundreds of feet tall, with rotation fast enough to uproot trees and hurl burning debris. The 2003 Canberra fires in Australia produced fire tornadoes strong enough to be classified as F2 on the Fujita scale. These phenomena are terrifying and fascinating in equal measure, showing how fire under extreme conditions can create its own weather, generating forces beyond what either fire or wind alone would produce. They represent fire at its most dynamic, most powerful, when it transcends simple combustion and becomes a force that bends physics to its will, creating structures of flame that tower and spin. Ancient peoples created fire through friction and percussion methods. Before matches, before lighters, before even flint and steel, how did humans create fire? Archaeological evidence and surviving traditional practices show two main methods: friction and percussion. Friction methods like the bow drill or hand drill involve rapidly rotating wood against wood. Friction generates heat, producing fine dust that eventually smolders, creating an ember that can be carefully nurtured into flame. This requires skill, knowledge of proper wood species, and persistence. It can take minutes of sustained effort. Percussion methods involve striking two stones together to create sparks. Flint and iron pyrite work particularly well. Flint's hardness chips off tiny fragments of pyrite that oxidize rapidly in air, producing sparks hot enough to ignite tinder. Both methods require practice and favorable conditions: dry wood, proper tinder, sheltered locations. The fact that humans in diverse locations independently developed these techniques speaks to fire's fundamental importance. Creating fire from raw materials, pulling flame from wood and stone, must have seemed like magic, a sacred act that connected humans to transformative power. Matches were invented relatively recently in human history. For most of human history, creating fire meant work friction, percussion, or carefully maintaining existing fires. The match, that simple tool we take for granted, appeared only in the 1800s. Early matches were dangerous, containing toxic materials and prone to accidental ignition. The safety match, designed to ignite only when struck on a special surface, became practical in the mid-1800s. This invention transformed daily life. Fire became instantly available to anyone with matches, democratizing flame, making light and heat accessible with a simple strike. No longer did people need to maintain fires continuously or possess fire-making skills. The match made fire pocket-sized and portable, available anytime. It's difficult to overstate this change. Lighting a lamp, starting a stove, smoking tobacco activities that once required preparation and skill became trivial. The match represents a key moment when technology separated humans further from direct engagement with fire's creation, making it a commodity rather than an achievement. Yet in that trade, we gained convenience and lost ancient knowledge. The Olympic flame travels thousands of miles, kept continuously burning. Since ancient Greece, fire has symbolized continuity and sacred tradition. The modern Olympic Games revive this symbolism with the Olympic flame, lit in Olympia, Greece, using focused sunlight and a parabolic mirror, then carried by relay to the host city. This flame travels thousands of miles over weeks or months, passing from torchbearer to torchbearer, crossing continents and oceans. At no point is it allowed to extinguish backup lanterns carry the same flame as insurance. The tradition connects modern games to ancient predecessors, creating continuity across millennia. The flame's journey becomes theater, celebration, and ritual combined. When it finally lights the Olympic cauldron at opening ceremonies, it represents the successful journey, the gathered effort of thousands, and the beginning of competition. That single flame links athletes to history, to tradition, to the ancient Greek ideal of human excellence. Its fire is symbol elevated to international celebration, showing how deeply flame remains embedded in human culture and meaning-making. Eternal flames burn at memorial sites around the world. Some fires are meant never to be extinguished. Eternal flames burn at memorials, monuments, and sacred sites across the globe, honoring the dead, commemorating events, or marking religious significance. The eternal flame at John F. Kennedy's grave, the flame of remembrance at war memorials, and sacred fires in temples and churches burn continuously, tended and maintained year after year, decade after decade. These flames carry symbolic weight. Their continuity represents memory that must not fade, sacrifice that must not be forgotten, presence that remains despite loss. Maintaining eternal flames requires dedication. Someone must ensure fuel supplies, protect flames from weather, relight if extinguishing occurs. This tending becomes ritual itself, an act of remembrance and care. The eternal flame transforms fire from temporary phenomenon into permanent symbol, defying combustion's natural tendency to consume and conclude. In doing so, it captures something essential about human nature, our desire to make meaning persist, to create permanence in an impermanent world, to keep light burning against darkness. Fireworks combine fire with chemistry to create aerial art. Fireworks transform fire into celebration, using combustion to launch shells of precisely engineered chemical compounds into the sky. When ignited, these compounds burn in specific colors: copper for blue, strontium for red, sodium for yellow, creating brilliant bursts of colored light. The shells contain multiple sections that ignite in sequence, producing complex patterns, bursts, weeps, palms, rings, and more. Getting fireworks to explode at the right altitude, to produce particular colors in specific patterns, requires careful chemistry and engineering. Ancient Chinese invented gunpowder and began creating fireworks over 1,000 years ago. The technology spread globally, evolving into today's spectacular displays. Modern firework shows synchronize hundreds or thousands of individual shells, choreographed to music, creating ephemeral art painted with fire across the night sky. Fireworks represent playful mastery of combustion, taking fire's power and beauty and amplifying it, making flames dance in ways impossible naturally. Their pure celebration, fire transformed from survival tool to aesthetic experience. Glass forms when sand melts and cools, shaped by fire's heat. Fire enables one of humanity's most beautiful material transformations, the creation of glass. Sand, primarily silicon dioxide, melts at extreme temperatures around 1,700 degrees Celsius. When it cools, instead of crystallizing back into sand, it can form glass, an amorphous solid that's neither crystal nor liquid, frozen in a state between. Ancient peoples discovered this process, perhaps noticing glass forming in intense campfires on sandy beaches. Glassmaking became sophisticated art, with glassblowers using furnaces to maintain precise temperatures, gathering molten glass on pipes, and shaping it through breath and tools while it remained workable. The process requires deep understanding of fire and temperature. Too cool, and glass becomes stiff and unworkable. Too hot, and it flows uncontrollably. Master glassblowers work in the narrow window, where glass responds to manipulation, creating objects from practical bottles to artistic masterpieces. Glass represents fire's creative power, its ability not just to destroy, but to transform, taking common sand and creating transparent, beautiful, useful material that has shaped human civilization. Pottery hardens in kilns through fire's transformative power. Clay, when shaped and dried, remains fragile and water-soluble. Fire transforms it into something permanent. Pottery making, one of humanity's oldest crafts, depends entirely on fire's ability to change material at the molecular level. In kilns, temperatures rise to 900 to 1,300 degrees Celsius or higher, depending on the clay and desired result. At these temperatures, water molecules bound chemically within clay, the structure are driven off, and the material undergoes irreversible changes, hardening into ceramic. The potter controls not just temperature but also atmosphere. Oxygen-rich oxidation fires produce different colors and finishes than oxygen-poor reduction fires. Ancient potters learned through experience how to build kilns, how to stack pots for even heating. When firing was complete, they created temperature indicators from clay cones that bend at specific heats. Pottery allowed food storage, cooking vessels, artistic expression, and containers for everything from water to precious oils. None of it would exist without fire's transformative power, its ability to permanently alter materials, to make soft clay stone hard and water resistant. Metalworking transformed human civilization through fire's mastery. The ability to shape metal, first copper, then bronze, then iron, and steel fundamentally changed human societies. Metalworking requires fire hot enough to melt or soften metals, temperatures achievable only with well-designed furnaces and proper fuels. The Bronze Age began when peoples learned to smelt copper and tin, combining them into bronze, an alloy harder than either pure metal. Iron working required even higher temperatures and more sophisticated techniques. Charcoal-fueled forges and later coal-fired blast furnaces enabled the iron and steel that built the industrial world. Every metal tool, weapon, ornament, and machine component begins with fire. Blacksmiths became essential community members, masters of the ancient partnership between fire and metal. Watching a blacksmith work heating iron to bright orange, hammering it into shape, quenching it in water with explosive hissing, is to witness fire-enabled transformation, raw ore becoming refined tool. Our modern world, with its buildings, vehicles, and infrastructure, ultimately rests on fire's ability to make stone yield up metal and to make that metal malleable enough for human purposes. The sun itself is a massive ball of nuclear fire. When we think of fire, we usually picture flames on Earth, wood burning, candles glowing, hearths radiating warmth. But the most significant fire in our existence burns 93 million miles away. The sun is essentially a gigantic nuclear furnace where hydrogen atoms fuse into helium under extreme pressure and temperature, releasing enormous energy. This isn't chemical combustion like earthly fire, but nuclear fusion, a far more powerful process. Yet the principle remains similar. Fuel transforms, energy releases, and light and heat emerge. The sun has burned for 4.6 billion years and will continue for billions more, its nuclear fire sustained by gravitational pressure compressing its core. Every bit of warmth you feel from sunlight, every photon that lights the day, comes from this stellar fire. Without it, Earth would be a frozen, lifeless rock drifting in darkness. The sun reminds us that fire, in various forms, powers existence itself. Stars across the universe are distant fires burning in the void. Our sun is not unique. Every star visible in the night sky is another nuclear furnace, another sun burning through its fuel across unimaginable distances. Some stars burn hotter and brighter than our sun, massive blue giants that exhaust their fuel in mere millions of years. Others burn cooler and dimmer, red dwarfs that will smolder for trillions of years long after our sun has died. Each star is a sphere of plasma, where nuclear fusion transforms matter into energy, creating the light that travels across space to reach our eyes. Stars are born in clouds of gas and dust, gravitational collapse, heating their cores until fusion ignites. They live for eons, steadily burning, then die in various ways depending on their size, some fading gradually, others exploding spectacularly. Stars are cosmic fires, scattered throughout the universe, each one a beacon of nuclear combustion. When we look at stars, we see fire in its most fundamental form, stripped of familiar flame and reduced to pure physics, pure energy release. Lightning is essentially electrical fire in the atmosphere. Lightning represents another form of fire, not chemical combustion but electrical discharge, creating intense heat and light. When lightning strikes, the channel of ionized air reaches temperatures around 30,000 degrees Celsius, 5 times hotter than the sun's surface. This extreme heat causes the air to expand explosively, creating thunder. The visible lightning bolt is essentially a path of superheated, glowing air. Ancient peoples surely viewed lightning with awe and fear, seeing fire descend from the sky with devastating power. Many cultures associated lightning with gods and divine anger. We now understand it as electrical imbalance between clouds and ground seeking equilibrium. But the phenomenon remains impressive. Lightning can ignite fires, as we've discussed, but it is itself a form of fire, a brief, intense release of energy, creating heat and light. It shows that fire exists in forms beyond familiar flames, that the principles of energy, released through rapid transformation, apply across different physical processes. Street. Elmo's fire glows on ship masts and aircraft during storms. Sometimes during thunderstorms, sailors reported seeing ghostly blue or violet flames dancing on ship masts, rigging, and other pointed surfaces. This phenomenon, called Street Elmo's fire, after the patron saint of sailors, isn't actually fire at all, though it glows and flickers like flame. It's a corona discharge, electrical current flowing from the atmosphere through pointed objects, ionizing the air and making it glow. The effect appears during thunderstorms when electrical fields become intense. Aircraft pilots sometimes see it on windshields and wingtips. To observers unfamiliar with the physics, it looks like fire that doesn't burn, blue-white flames that dance on metal and wood, without consuming anything. Ancient sailors considered it a good omen, a protective sign. Modern understanding reveals electrical principles, but the visual remains striking, another reminder that fire-like phenomena can arise from different physical processes, that light and apparent flame can emerge from electricity as well as combustion. Will-o'-the-wisps may be spontaneous marsh gas combustion. Throughout history, people reported mysterious lights, hovering over swamps and marshes, floating balls of flame that appeared and vanished without explanation. Called will-o'-the-wisps, jack-o'-lanterns, or corpse candles, they sparked superstitious beliefs about spirits and the supernatural. One scientific explanation involves marsh gas, methane, and phosphine produced by decaying organic matter in wetlands. Under certain conditions, these gases might ignite spontaneously, creating small, brief flames that drift with air currents. The phenomenon is rare and difficult to study, and debate continues about exact mechanisms. Other explanations involve bioluminescence or misidentified mundane lights. Regardless of cause, the cultural impact was significant. These mysterious lights fed folklore about spirits, leading travelers astray, about fairy lights and supernatural omens. They represent fire at its most mysterious, flames appearing without obvious source or reason, burning briefly before vanishing. Whether chemical combustion or other phenomena, will-o'-the-wisps remind us that fire can surprise, can appear in unexpected places, behaving in ways that seem magical even when science offers explanations. Volcanoes release Earth's inner fire to the surface. Deep within Earth, temperatures reach thousands of degrees, hot enough to melt rock into magma. Volcanoes are essentially release valves for this internal heat, places where Earth's molten interior breaks through to the surface. When volcanoes erupt, they pour forth lava, liquid rock, glowing with heat, flowing like incandescent rivers. This isn't combustion in the chemical sense, but it shares fire's essential qualities: extreme heat, transformation of materials, light emission, and destructive power. Lava flows consume everything in their path, setting fires when they encounter vegetation. Volcanic gases can ignite, creating actual flames. Ancient peoples who witnessed eruptions must have thought they saw the earth itself on fire. Mountains vomiting flame and molten stone. They weren't wrong. Volcanoes are Earth's fire made manifest, proof that beneath the solid ground we trust, intense heat churns, waiting for pathways to the surface. Every volcanic eruption is ancient fire from Earth's formation, primordial heat still escaping billions of years later. Lava glows from intense heat, not from burning. When lava flows from volcanoes, it glows brilliant, orange, yellow, or even white, depending on temperature. This glow comes from incandescence, the emission of light from intensely heated matter, not from combustion. Lava is molten rock, too hot to touch, hot enough to ignite anything flammable it contacts, but it isn't burning itself. The glow we see is heat made visible, photons released by atoms vibrating with thermal energy. As lava cools, it changes color, shifting from white-hot through yellow and orange to red, then finally dark as it solidifies. This color progression mirrors fire's colors, both following the same physics of blackbody radiation, where hotter objects emit light at shorter wavelengths. Watching lava flow is mesmerizing. It moves like thick liquid, crusting over, then breaking open to reveal brilliant heat beneath. It's fire's aesthetic without fire's chemistry, showing that heat alone, at sufficient intensity, creates the glow and warmth we associate with flame. Lava is Earth's version of fire, geological rather than chemical, but equally powerful and primarily fascinating. Geothermal springs show Earth's warmth bubbling to the surface. Not all Earth's internal heat appears as dramatic as volcanoes. Geothermal springs and geysers provide gentler reminders that fire exists beneath our feet. Water seeping underground encounters hot rock, heats to extreme temperatures, and returns to the surface as hot springs or, when pressure builds sufficiently, explodes upward as geysers. These phenomena cluster in volcanically active regions where Earth's heat lies closer to the surface. Ancient peoples settled near hot springs, using them for warmth, cooking, and healing. The Romans built elaborate bath complexes around natural hot water sources. Today, geothermal energy provides heat and electricity, tapping Earth's fire for human use. Yellowstone's geysers, Iceland's hot springs, and similar features worldwide demonstrate that fire, or at least extreme heat, isn't just something we create, but something Earth provides. The planet itself is warm, still cooling from its fiery birth billions of years ago, and that ancient heat occasionally touches the surface, reminding us of the furnace below. The Earth's core remains molten from primordial heat and radioactive decay. Earth's center, thousands of miles beneath our feet, remains intensely hot, around 5,000 to 7,000 degrees Celsius, as hot as the sun's surface. This heat comes partly from Earth's formation, when countless impacts compressed and heated material into a planet. But Earth should have cooled by now, if that were the only source. Instead, radioactive decay within Earth's interior elements like uranium, thorium, and potassium slowly breaking down, continuously generates heat. This internal fire drives plate tectonics, powers volcanoes, creates Earth's magnetic field, and maintains our planet as a geologically active world. Without this inner fire, Earth would be cold and dead, like Mars appears to be, without volcanic activity or continental drift. Our planet lives because fire burns within it. A slow nuclear fire from decaying elements combined with primordial heat still dissipating. We walk on a thin crust above a world of heat and molten rock, a shell over fire that will burn for billions of years more. Combustion engines transformed transportation by harnessing controlled explosions. The internal combustion engine represents human mastery of fire taken to mechanical precision. In car engines, carefully timed explosions of gasoline vapor occur thousands of times per minute, each controlled burst, pushing pistons that turn wheels. This is fire reduced to predictable, repeatable cycles. Combustion so precisely controlled it becomes reliable power. The engine's invention revolutionized transportation, making personal mobility available to millions. Ships, planes, trains, and vehicles all rely on controlled combustion, on fire's power channeled into useful work. Engineers design engines to optimize combustion efficiency, to extract maximum energy from fuel while minimizing waste and pollution. Every time you drive, ride, or fly, you're trusting controlled fire to provide power. The engine is distant descendant of the first human-controlled flames, showing our species' journey from simply keeping fire alive to commanding it with split-second precision, making it perform exactly as needed, reliably, over and over. Jet engines use continuous combustion to generate thrust. Unlike piston engines with their cyclic explosions, jet engines maintain continuous combustion. Air is compressed, mixed with fuel, ignited, and the expanding hot gases are expelled rearward, providing forward thrust. The combustion chamber inside a jet engine burns constantly during flight, a controlled inferno channeled through carefully engineered passages. Jet fuel burns at extremely high temperatures, and the engines must withstand this constant heat while maintaining precision tolerances. The whine and roar of a jet engine is the sound of continuous combustion, of fire turned into sustained power. Jet propulsion allowed speeds impossible with propellers, enabled modern air travel, and made our world smaller and more connected. Standing near a jet engine's exhaust feels the heat of that contained fire. These engines represent fire as perpetual force, not flickering flame or cyclic explosion, but sustained, constant burn combustion that doesn't start and stop but persists, controlled and directed, converting chemical energy into motion with remarkable efficiency. Rockets burn fuel in environments without oxygen by carrying oxidizers. Fire usually needs atmospheric oxygen, but rockets must work in the vacuum of space where no air exists. They solve this by carrying oxidizer, usually liquid oxygen, along with fuel. When combined in combustion chambers, the two react exactly as fire would in atmosphere, releasing energy that propels exhaust gases at tremendous speeds. Newton's third law provides thrust. Gases exit one direction, rocket goes the other. The Saturn V rocket that took humans to the moon burned kerosene and liquid oxygen in its first stage, releasing more power than dozens of jet engines combined. Watching a rocket launch is seeing fire at titanic scale. Flames bright enough to illuminate the landscape, roar loud enough to shake the ground miles away. The exhaust plume stretches hundreds of feet, glowing white-hot. Rockets represent fire unchained from Earth's atmosphere, combustion so powerful and self-contained it can push humans off the planet entirely. Their triumph of controlled fire, taking the most challenging environment, airless space, and making combustion work anyway through chemistry and engineering. Fire has been weaponized throughout human history. Humans quickly realized fire's potential as a weapon. Greek fire, a Byzantine military secret, was an incendiary liquid that burned on water, terrifying naval enemies. Flaming arrows, fire ships, burning oil poured from castle walls throughout history. Militaries weaponized combustion. Flamethrowers project burning liquid at enemies, a horrifying weapon that violates modern warfare conventions. Incendiary bombs destroyed cities during World War II, firestorms consuming entire urban areas. Modern militaries use white phosphorus, thermite, and other incendiary materials. Fire as weapon exploits its most terrifying qualities. It spreads uncontrollably, causes excruciating injury, destroys resources and infrastructure, and creates psychological terror. The deliberate use of fire against humans represents dark application of something otherwise beneficial. It shows fire's neutral nature, a tool that can warm and feed us or destroy us, depending on intent. The same combustion that cooks our meals and heats our homes becomes weapon when directed with hostile purpose, reminding us that most tools can serve creation or destruction. Napalm burns at extreme temperatures, sticking to surfaces. Among the most notorious incendiary weapons, napalm combines fuel with thickening agents to create a gel that sticks to surfaces while burning at extreme temperatures. Developed during World War II, it was used extensively in conflicts through the 20th century. Napalm's effectiveness as weapon comes from its persistence. It adheres to whatever it contacts and continues burning intensely, difficult to extinguish. Its use raises ethical questions about proportionality and suffering in warfare. The word napalm itself evokes horror, symbolizing fire weaponized to maximum deadly effect. It represents extreme example of how understanding combustion chemistry enables creation of substances optimized purely for destruction. Yet the same chemistry that creates such weapons also produces useful materials like solid rocket fuels and controlled incendiaries for agricultural burning. Science itself is neutral. Application determines whether knowledge serves constructive or destructive ends. Napalm stands as a reminder that fire's power can be amplified through chemistry into forms far deadlier than natural combustion. Fire suppression technology has advanced dramatically. As humans built closer together, fire became an existential threat to communities. Cities burned repeatedly throughout history. Rome, London, Chicago, San Francisco, all experienced catastrophic fires that destroyed vast areas. These disasters drove innovation in fire suppression. Modern fire departments use powerful pumps to deliver water at high pressure. Foam suppressants smother fires by excluding oxygen. Dry chemical extinguishers interrupt combustion chemistry. Halon and similar gases were developed for special applications like aircraft and computer rooms, though some were phased out due to environmental concerns. Automatic sprinkler systems respond to heat, releasing water before fires grow. Fire-resistant building materials slow combustion spread. Building codes mandate exits, compartmentalization, and fire detection systems. This entire technological apparatus exists to counter fire's threat. The effort put into fire suppression shows both fire's danger and our determination to coexist with combustion. Using fire's benefits while minimizing its risks, we've engineered elaborate systems to prevent, detect, and extinguish unwanted fire, while maintaining controlled fire for countless purposes. Smoke detectors save thousands of lives by providing early warning. Most fire deaths come from smoke inhalation rather than burns. Toxic gases, carbon monoxide, hydrogen cyanide. Others cause unconsciousness and death before flames reach victims. Smoke detectors, which became common in homes only in recent decades, address this by detecting smoke and sounding alarms before conditions become lethal. These simple devices have saved countless lives by waking sleeping occupants or alerting people to fire in distant parts of buildings. Ionization detectors sense changes in electrical current caused by smoke particles. Photoelectric detectors use light beams disrupted by smoke. Both types respond to fire's presence long before human senses might notice. The widespread adoption of smoke detectors represents public health triumph, a technology that reduces fire deaths significantly at minimal cost. It shows how understanding fire's dangers enables protective technology. That small disc on your ceiling, easy to ignore, stands guard continuously, ready to sound alarm if combustion begins, giving precious minutes to escape fire's rapid spread. Fire extinguishers attack different sides of the fire triangle. Fire extinguishers come in several types, each designed for specific fire classes. Water extinguishers cool fires, removing heat, effective on wood, paper, and similar materials, but dangerous on electrical or grease fires. CO2 extinguishers displace oxygen, smothering fires without leaving residue. Dry chemical extinguishers interrupt combustion chemistry, stopping the reaction itself. Foam extinguishers both cool and smother. Class ratings indicate appropriate uses. Class A for ordinary combustibles, Class B for flammable liquids, Class C for electrical fires, Class D for combustible metals, Class K for kitchen grease fires. Using the wrong extinguisher can worsen fires. Water on grease fires spreads burning oil. Water on electrical fires can electrocute the user. Understanding fire types and appropriate suppression methods represents accumulated knowledge from disasters and experiments. Every extinguisher exists because someone studied how fire behaves with specific materials and developed countermeasures. These cylindrical red canisters, ubiquitous in buildings worldwide, embody centuries of learning how to fight fire effectively and safely. Wildfires can create their own weather patterns. Large wildfires generate so much heat they influence atmospheric conditions, sometimes dramatically. The rising column of hot air and smoke from a major fire acts like a chimney, drawing in air from surrounding areas and creating strong winds that feed the fire further. In extreme cases, this can form pyrocumulonimbus, clouds, thunderstorms created by the fire itself. These fire-generated storms can produce lightning that starts additional fires, creating a feedback loop. The rising heat can even spawn fire tornadoes, as mentioned earlier. Massive wildfires create their own wind patterns that can change direction unpredictably, making firefighting extremely dangerous. The smoke plumes from large fires can reach the stratosphere, circling the globe and affecting air quality thousands of miles away. These megafires represent fire at its most powerful and uncontrollable, burning with such intensity that they transcend simple combustion and become weather events, climatic phenomena that shape their environment on regional scales. They remind us that fire, unleashed fully, commands forces beyond human control. The Great Fire of London burned for 3 days in 1666. In September 1666, fire began in a bakery on London's Pudding Lane. Over 3 days, it consumed about 13,000 houses, 87 churches, including St. Paul's Cathedral, and most of the city's administrative buildings. The fire burned so hot, it melted pottery and even stone. The densely packed wooden buildings, narrow streets, and strong winds created perfect conditions for fire spread. Despite the destruction, remarkably few deaths were recorded, perhaps only 6, though the true toll may have been higher among the poor whose deaths went unrecorded. The Great Fire, paradoxically, improved London. The city rebuilt with wider streets, stone and brick buildings, and better planning. Building codes emerged directly from this disaster. The fire demonstrated the danger of dense urban development with flammable materials and inadequate fire suppression. It stands as cautionary tale and as example of how catastrophe can drive positive change. The monument commemorating the fire still stands in London, a reminder that fire shaped the city literally and metaphorically. The Great Chicago Fire of 1871 may have been helped by comet debris. The Great Chicago Fire burned from October 8 to 10, 1871, destroying much of the city. Legend blames Mrs. O'Leary's cow kicking over a lantern, though this is likely apocryphal. What's more interesting is that on the same night, a similar fire devastated Peshtigo, Wisconsin, killing far more people in a less remembered disaster. Some researchers speculated that comet debris entering atmosphere might have started multiple fires, though this theory lacks strong evidence. More likely, both fires resulted from extreme drought conditions, strong winds, and wood construction prevalent at the time. Chicago, like London before it, rebuilt stronger. The fire led to innovations in fireproof construction, including steel frame buildings that would define the modern skyscraper. From disaster came renewal and progress. These great urban fires shaped modern fire codes, insurance industries, and city planning worldwide. They taught expensive lessons about fire's power in urban environments and the importance of prevention and suppression systems. Forest fire seasons are lengthening due to climate changes. In many regions, wildfire seasons that once lasted a few months now extend across half the year or more. Warmer temperatures, dry fuels earlier in spring, and maintain dry conditions later into fall. Reduced snowpack means less moisture in soil and vegetation. These changes create conditions favorable for fire over longer periods. Combined with fuel accumulation from decades of fire suppression, this creates potential for more frequent and severe wildfires. Some regions experience fires in seasons that previously were too wet or cool. This shift affects ecosystems that evolved with predictable fire cycles. stresses firefighting resources, and threatens communities built in fire-prone areas. Scientists document these changes through statistical analysis showing clear trends toward longer fire seasons and larger burned areas. While any single fire can't be attributed to climate alone, the broader pattern is unmistakable. Fire seasons responding to climate represent feedback loop. Fires release carbon dioxide, contributing to warming that creates conditions for more fires. Understanding this cycle is crucial for adapting fire management strategies to changing reality. Firefighters can become trapped in burnover situations. Wildfires can move with terrifying speed, especially when wind shifts or fire reaches fuel-rich areas. Firefighters working to contain fires sometimes find themselves suddenly in the fire's path as conditions change. This situation, called a burnover, is every wildland firefighter's nightmare. When it occurs, firefighters deploy emergency fire shelters, tent-like, aluminum foil structures they climb inside, hoping to survive the passing flames. These shelters reflect radiant heat and trap breathable air, but their last resort, not guarantee of survival. Many firefighter deaths occur in burnovers when fires move faster than crews can retreat. The 1,949-man Gulch Fire, 1,994 South Canyon Fire, and 2013 Yarnell Hill Fire are among many tragedies where crews were overrun. These events led to improved training, better safety protocols, and refined understanding of fire behavior. But they also remind us that fighting wildfire is inherently dangerous, pitting human courage against fire's unpredictable power. Those who battle wildfires walk daily into situations where fire's ancient force can turn deadly in moments. Hotshots and smoke jumpers are elite wildland firefighters. Among wildland firefighters, certain crews represent the most highly trained and skilled. Hotshots are interagency teams that travel wherever fires burn most intensely, working long shifts in difficult terrain to build fire lines and conduct burnout operations. They're physically fit, highly trained, and experienced in fire behavior. Smoke jumpers parachute into remote fires, jumping from aircraft into wilderness areas where roads don't reach. They carry tools, food, and equipment, then hike out after containing fires, sometimes walking dozens of miles. Both groups represent modern warriors against wildfire, using knowledge, strength, and courage to battle flames in challenging conditions. The tradition connects to ancient relationships between humans and fire, where once we might have fled from wildfire, now we have specialists who run toward it, who understand fire deeply enough to predict its behavior and counter its spread. Their work saves lives, property, and natural resources, though it comes with significant personal risk. These elite firefighters embody mastery of fire at professional and physical extremes. Slash and burn agriculture uses fire to clear and fertilize land. In tropical and subtropical regions, slash and burn agriculture has been practiced for millennia. Farmers cut vegetation, let it dry, then burn it before planting crops. Fire clears land quickly, kills seeds and pests, and deposits nutrients from plants directly into soil as ash. For several years, crops grow well in the enriched soil. Eventually, nutrients deplete, and farmers move to new plots, allowing old ones to regrow. When done sustainably with long fallow periods, this system can maintain forest health. However, population pressure has shortened fallow cycles in many regions, degrading forests and releasing significant carbon dioxide. Additionally, fires sometimes escape control, burning larger areas than intended. The practice represents ancient fire use for agriculture, turning forest into temporarily productive farmland. It shows fire's role in human land management and food production, though like many fire uses, It requires balance and knowledge to avoid degradation. The smoke from slash and burn fires can affect air quality regionally, making this practice increasingly controversial in densely populated areas. Charcoal from controlled burning improves soil fertility. Recently, scientists have recognized that biochar charcoal, created through controlled burning of organic material, can significantly improve soil quality. Indigenous peoples in the Amazon created terra preta, black earth, through adding charcoal to soil, creating fertility that persists centuries later. Charcoal's porous structure provides habitat for beneficial microorganisms and helps soil retain nutrients and water. Unlike organic matter that decomposes quickly, charcoal remains stable for hundreds or thousands of years, making it an effective carbon sequestration method. Creating biochar involves heating organic waste in low oxygen conditions, similar to traditional charcoal making. The process generates heat that can produce energy while creating useful soil amendment. This represents fire used not just destructively, but constructively, transforming waste material into something that enhances soil productivity while locking carbon away. It's ancient knowledge rediscovered and scientifically validated, showing that fire, when controlled precisely, can contribute to sustainability rather than merely consuming resources. Biochar production turns fire into a tool for soil health and climate mitigation. Indigenous peoples used fire to shape landscapes for thousands of years. Before European colonization, indigenous peoples across multiple continents practiced sophisticated fire management. In North America, regular burning maintained meadows for game, promoted growth of food-producing plants, reduced wildfire risk, and created diverse habitat mosaics. In Australia, Aboriginal peoples used fire so extensively that the landscape itself evolved in response, with fire-adapted species dominating. These burning practices weren't random but carefully timed and located based on accumulated knowledge of plant cycles, animal behavior, and fire effects. When colonizers suppressed indigenous burning, landscapes changed dramatically, often becoming overgrown and more susceptible to catastrophic fires. Modern land managers increasingly recognize the wisdom in traditional burning practices and work with indigenous communities to revive controlled burning. This shows that fire is not simply destructive force to be suppressed, but tool that, used with knowledge and care, maintains healthy ecosystems. Indigenous fire use represents thousands of years of experimentation and observation, a deep understanding of fire's ecological role that modern science is only beginning to fully appreciate. Fire has profound spiritual significance across cultures. Humans have treated fire as sacred since we first controlled it. Zoroastrianism maintains eternal flames in fire temples, considering fire pure and holy. Hindu ceremonies use fire as connection to divine, with home hearths traditionally never fully extinguished. Buddhism uses butter lamps, flame representing enlightenment. The Olympic flame derives from ancient Greek sacred fires. Many indigenous traditions consider fire a gift from deities or culture heroes who stole it from gods for humanity's benefit. Fire appears in religious ceremonies worldwide, candles in churches, bonfires at solstices, cremation pyres releasing souls, and countless other contexts. This universal reverence likely stems from fire's transformative power, its brightness in darkness, and its essential role in survival. Fire transforms but also seems alive, moving, consuming, growing. It provides warmth like the sun, but on human scale. These qualities make fire a natural symbol for divine presence, spiritual transformation, and the sacred. That fire appears across religions and cultures as spiritual symbol suggests deep human recognition of its profound importance. Candles create calm through flickering light and scent. A simple candle affects mood and atmosphere in ways humans find deeply comforting. The flickering flame provides gentle, moving light that contrasts with harsh, steady, artificial lighting. Humans seem naturally drawn to this movement, perhaps because our ancestors spent countless generations around fires. Scented candles add aromatherapy effects, with fragrances affecting mood through olfactory pathways. The ritual of lighting a candle, the slight resistance of the match, the care in bringing flame to wick, the moment of ignition creates mindful pause in busy days. Candles mark celebrations, religious observances, and remembrance. They transform ordinary spaces into special ones. The candle market thrives because these simple objects, wax and wick, connect us to something ancient and essential. Their fire domesticated to its gentlest form, contained and controlled, beautiful rather than threatening. In a candle's glow, we feel the same warmth our ancestors felt, the same sense of safety and comfort that fire has provided across millennia. That simple flame still speaks to something deep in human psychology. Bonfires bring communities together in celebration. Large outdoor fires have historically served as gathering points. Solstice bonfires mark seasonal transitions. Victory fires celebrate triumphs. Beach bonfires create social space where people share food, stories, and companionship. The bonfire's heat creates a defined circle, comfortable close by, too hot, very near, too cool far away, naturally organizing people into community space. Faces visible in firelight, while surroundings fade to darkness. Focus attention inward on the group. Bonfire gatherings feel special, set apart from ordinary life. The flames provide entertainment through their movement, crackling sounds, and occasional showers of sparks. Building the fire becomes group activity, contributing wood, an act of participation. These fires connect participants to ancient traditions, to the countless human gatherings around flame throughout history. Modern bonfire parties, beach fires, and campfire circles continue traditions tens of thousands of years old. Despite all our technology, we still gather around fire, still find comfort and joy in flame's warmth and light, still use fire to mark occasions as special and communal. Campfires remain central to outdoor experiences. Despite modern camping equipment, LED lanterns, portable stoves, battery-powered heaters, the campfire remains essential to outdoor experiences. Why? Partly tradition, partly practicality, but mostly because campfires provide something beyond utility. Their experience itself, connection to nature and to human history. Gathering around a campfire feels right in ways electric light doesn't replicate. Stories shared in firelight feel more meaningful. Food cooked over flame tastes different, better. The slight smoky smell that clings to clothes becomes souvenir of the experience. Children experience primal thrill of controlled flame, learning respect for fire's power. Campfires teach skills, building proper structure, choosing appropriate wood, maintaining right size, extinguishing completely. These skills connect us to ancestors, for whom fire meant survival. Even in recreational context, campfire maintains its power to center human experience, to create space for reflection, conversation, and connection. As long as humans venture outdoors, we'll build campfires, not just for warmth or light, but for what fire provides to the human spirit. Marshmallows over fire become beloved tradition. Something magical happens when you roast marshmallows over fire. The outside caramelizes and sometimes catches flame. The inside melts to liquid sweetness. The technique requires attention too close, and it ignites too far, and nothing happens. Perfect distance creates golden brown exterior and gooey center. This simple act connects children to fire in safe, controlled way, teaching respect for heat while creating positive associations. Marshmallow roasting is often first deliberate fire interaction for young people, memorable because it combines learning, slight danger, flames, and sweet reward. The tradition extends to s'mores, that campfire classic, combining marshmallow, chocolate, and graham crackers. These treats become inseparable from outdoor fire experiences. No one roasts marshmallows indoors over stoves. It requires open flame, outdoor setting, campfire atmosphere. The activity is participation in fire culture, a way of engaging with combustion that's playful rather than fearful. Through marshmallow roasting, generations learn that fire can be friend, not just danger, when treated with knowledge and respect. Fire poi and performance art transform flame into beauty. Fire dancers and performers use fire not for light or heat, but purely for aesthetic experience. Fire poi weights soaked in fuel and ignited, swung on chains, create trails of light through darkness. Fire staffs, hoops, and other props become tools for creating moving patterns of flame. Performers train extensively to handle fire safely, while creating beautiful, dramatic shows. The art form has ancient roots in various cultures, but has evolved into international community with competitions and festivals. Fire performance requires deep respect for combustion, understanding of fuels and safety, and mastery of movement. Done well, it's breathtaking. Human bodies creating flowing sculptures of light, ephemeral art that exists only in the moment it's performed. Fire performance elevates flame beyond utility into pure expression, showing fire's aesthetic potential. The courage required to perform with fire adds to the dramatic impact. Audiences instinctively recognize the risk, making performances thrilling and captivating. Fire becomes partner in artistic creation, element to be choreographed and controlled through skill and practice. Glass-blowing galleries let visitors watch fire shape art. Watching a master glassblower work is witnessing fire-enabled creation in real time. The artist gathers molten glass from a furnace burning at extreme temperatures, working quickly as gravity pulls the material while it remains soft. Through breath, tools, and practiced motion, a blob of glowing glass becomes delicate goblet, flowing sculpture, or useful bowl. The process is captivating the interplay of heat and skill, the transformation of formless molten material into deliberate shapes. The fire's role is essential but background. The furnace maintains precise temperature, allowing creation to proceed. Glass-blowing galleries invite observers to watch this ancient craft, demonstrating how fire enables art. The glow of hot glass, the precision required, the way form emerges from shapelessness, all of it creates mesmerizing show. This public demonstration of firecraft connects observers to traditions thousands of years old, while showcasing modern artistry. It shows fire not as danger or basic utility, but as crucial partner in human creativity, enabling beauty that couldn't exist without combustion's transformative heat. Pottery studios reveal clay's transformation through flame. Like glassblowing, pottery offers public glimpse into fire's creative power. Pottery studios often allow visitors to see kilns being loaded and fired, sometimes offering night firings where observers watch kiln temperatures rise, seeing glow through peepholes as heat transforms clay. The progression from fragile, dried clay to solid ceramic represents complete transformation, one-way change from which there's no reversing. This metamorphosis happens only through fire's heat. Watching this process, even understanding it scientifically, retains element of magic material, becoming fundamentally different through fire's action. Ancient potters must have seemed like wizards, commanding earth and flame to create objects that held water, stored food, served in ceremonies. Modern potters continue this tradition, using electric kilns or gas burners or traditional wood-fired kilns, each producing distinctive results. The surface effects, colors, and textures emerge from complex interactions between clay, glaze, atmosphere, and temperature. Fire doesn't just heat clay. It participates in creation, its specific characteristics affecting the art that emerges. Every pot, plate, and sculpture that went through kiln bears fire's mark. Blacksmith demonstrations show metal yielding to flame's heat. The clang of hammer on anvil, the hiss of hot metal in water, the glow of iron in forge blacksmith demonstrations transport observers to earlier eras, when metalworking was essential craft. Modern blacksmiths, practicing traditional techniques, show how fire makes metal workable, transforming rigid material into something that can be shaped. The smith reads temperature by color, knowing when metal reaches ideal heat for forming. This knowledge, accumulated over generations, represents deep understanding of fire's effects on materials. Watching metal bend and flow under controlled strikes demonstrates fire's enabling power. Without heat, the metal would simply break. With proper temperature, it becomes clay in the smith's hands. The partnership between human skill and fire's transformative heat produces tools, art, and practical objects. Blacksmithing demonstrations remind us that before mass production, fire and human muscle created everything metal, from nails to swords, horseshoes to gates. The craft survives partly as art, partly as practical skill, but mostly as living connection to how fire built civilization. Fireplaces and hearths anchor homes architecturally and emotionally. For most of human history, the hearth was literally the center of home. The fireplace provided heat, light, and cooking ability. Families gathered around it because that's where warmth and activity concentrated. Even after central heating and electric lighting made fireplaces functionally unnecessary, homes continued including them. Why? Because fireplaces provide more than utility. They create focal points, architectural anchors around which rooms organize. A fireplace makes a room feel complete, offers place for eye to rest, provides center for furniture arrangement. The symbolism matters too. Hearth represents home itself, safety, family, comfort. Real estate agents know homes with fireplaces command higher prices, even if buyers rarely use them. The crackling fire, dancing flames, radiant warmth, these remain psychologically powerful. In winter, lighting a fire transforms a house into a home. The effort involved carrying wood, arranging logs, tending flames creates ritual that marks time and season. Though most modern homes don't need fireplaces for survival, we include them anyway, honoring ancient connection between fire and dwelling, between flame and the meaning of home. Wood stoves provide efficient heating with proper operation. While fireplaces lose much heat up chimneys, wood stoves capture and radiate heat efficiently. Modern stoves achieve remarkable efficiency, extracting maximum energy from wood while minimizing smoke and particulates. Proper operation requires skill building appropriate fires, controlling air intake, maintaining temperatures that burn cleanly without overheating or smoldering. The stove becomes teacher, training operators to understand combustion through feedback of heat, smoke, and flame behavior. Families heating with wood develop intimate knowledge of fire, becoming daily practitioners of combustion management. They learn to read weather and plan accordingly, to select and season wood properly, to maintain equipment and clean chimneys. Wood heat connects users to forest and fire in direct, tangible ways. The warmth feels different from electric or gas heat, more present somehow, more conscious. Wood heat requires work, but offers rewards beyond warmth, competence, self-reliance, connection to natural cycles. In rural areas and cold climates, wood remains primary heating source for many, continuing relationships between humans and fire that stretch back to prehistory. Pellet stoves automate wood burning for modern convenience. For those wanting wood heat without traditional wood stoves' labor intensity, pellet stoves offer compromise. They burn compressed wood pellets, sawdust, and wood waste compacted into uniform cylinders. Augers automatically feed pellets from hoppers into burn chambers, and electronic controls regulate combustion for optimal efficiency. This automation means pellet stoves require less attention than traditional wood stoves while still burning renewable fuel. The pellets produce less ash and burn very cleanly when quality is high. However, the system requires electricity for controls and pellet feeding, and pellet supply chains can experience disruptions. The technology represents evolution in wood burning, applying modern engineering to ancient practice of heating with combustion. Pellet stoves show how fire use adapts. We maintain the essence of burning wood for heat while adding convenience and efficiency. The result feels less traditional, less connected to fire's ancient roots, but provides practical solution for modern users wanting renewable heat without constant tending. Gas fireplaces mimic flame with modern convenience. Many modern homes feature gas fireplaces that ignite at switch flip, producing flame without wood, smoke, or ash. These provide fireplaces visual appeal and some heat with minimal effort. Ceramic logs or glass media sit above gas jets, and flames dance convincingly, almost indistinguishable from real fires. Yet, something is lost. The fire isn't real combustion of solid fuel, but burning gas, controlled precisely by regulators and valves. There's no crackling, no wood scent, no need for tending. The convenience is undeniable, but the experience feels diminished, somehow less authentic. Gas fireplaces represent ultimate domestication of fire, reduced to appliance controlled by thermostat. They give us flame's appearance without its substance, fire's aesthetic without its character. This reflects modern relationship with fire. We want fire's benefits and beauty without its demands or risks. Gas fireplaces serve purposes well, but they're simulation rather than the real partnership between human and flame that characterized fire use throughout history. Their fire made so convenient, it becomes merely decoration, losing the engagement that made fire central to human experience. Fire pits extend outdoor living spaces into cooler seasons. Backyard fire pits have become increasingly popular, creating focal points for outdoor gatherings. These range from simple metal bowls to elaborate stone structures with seating built around them. The fire pit serves multiple purposes. It provides warmth, allowing outdoor use during cool evenings, creates ambience with dancing flames, and offers spot for cooking s'mores or roasting hot dogs. Like ancient hearths, fire pits organize social space, defining where people gather and creating natural circles for conversation. Building and tending the fire becomes shared activity, with family members or friends contributing wood and adjusting logs. Fire pits represent bringing hearth outdoors, reclaiming direct fire experience in age when indoor fireplaces often go unused. Their small concession to ancient human need to gather around flame, to share fire's warmth and light with companions. The fire pit boom suggests that despite modern comforts, we still crave fire's presence, still find gathering around flames satisfying in ways other activities can't match. We may not need fire for survival anymore, but we apparently still need it for something deeper, more psychological. Tiki torches and outdoor oil lamps extend daylight naturally. In outdoor spaces, tiki torches and oil lamps provide lighting that feels more natural than electric alternatives. The flame's warm glow, its movement, and its relative dimness compared to electric lights create atmosphere impossible to replicate artificially. These flames mark pathways, define areas, and add romance to outdoor dining or entertaining. The slight smoke from citronella torches also repels insects, adding practical function. Unlike electric lights that illuminate broadly and harshly, flame-based lighting creates pools of light surrounded by relative darkness, making spaces feel intimate and special. Using these requires basic fire skills, fueling lamps, lighting wicks, ensuring stable placement, engaging users with fire directly. While purely decorative in most applications, these flames connect us to how humans illuminated night for thousands of years before electricity. They remind us that fire provided humanity's only nighttime lighting for most of history. Walking a path lit by torches or dining by lantern light briefly transports us to earlier eras when fire was the only option, helping us appreciate both what we've gained through technology and what we've lost in distancing ourselves from direct fire relationship. Candelabras and chandeliers once held dozens of candles. Before gas and electric lighting, wealthy homes illuminated rooms with elaborate candelabras holding multiple candles. Grand chandeliers might support dozens of candles, requiring servants to light each one and replace them as they burned down. This was expensive. Candles required tallow or beeswax, both costly, and large households went through enormous quantities. The very rich used spermaceti from Wales, even more expensive but providing clearer, brighter flame. Lighting many candles for an event was showing wealth and status, quite literally burning money for illumination. These lighting systems also posed fire risks. Exposed flames near fabric, wood, and paper caused frequent fires. Yet, they were the best option available, so people accepted risks and costs. Today's decorative chandeliers echo these origins, often designed for candles, even when fitted with electric lights. The forms persist because they're beautiful, but they remind us how dramatically fire's role in lighting has diminished. What once required careful management, significant expense, and constant attention now requires only flipping switches, taking for granted what our ancestors considered luxury. Street lamps once required daily lighting by lamplighters. Before electric streetlights, cities employed lamplighters who walked routes every evening, lighting gas lamps as darkness fell. They carried ladders and poles with lit tapers, reaching each lamp to open valves and ignite the gas flame. In morning, they'd return to extinguish lamps. This job persisted from the early 1800s into the 1900s as gas lighting spread through cities. The lamplighter became a romantic figure in literature and art, representing the boundary between day and night, bringing light to streets as darkness descended. Gas lamps provided dim, flickering illumination, nothing like modern streetlights, but they made cities safer and extended usable evening hours. The infrastructure required gas mains, lamp posts. Maintenance systems represented major urban investment. A few cities maintain gas lamps in historic districts, often automated now but preserving the aesthetic. These remind us that illuminating cities with fire was normal for only a brief period, a transitional technology between open flames and electricity. The lamplighter's daily ritual represents human effort required to provide light through combustion, effort we no longer notice because electric lights simply turn on automatically. Edison's light bulb began replacing fire for illumination. Thomas Edison's development of practical incandescent light bulbs, starting in 1879, marked a turning point in fire's role in human life. For the first time, bright light could be generated without combustion, without flame, without smoke or fire risk. Early adoption was slow. Electric systems required expensive infrastructure, and early bulbs were fragile and short-lived. But advantages were clear. Electric light was safer, cleaner, easier to control, and ultimately cheaper than gas or oil lamps. Within decades, electric lighting spread through developed world, transforming night from dangerous dark period to illuminated extension of day. This change was revolutionary. Work patterns shifted, social life expanded, cities became safer. Fire's ancient role as sole light source ended. We still use candle power and similar terms referencing fire-based lighting, linguistic fossils of fire's former dominance. The transition from flame to electric light perhaps marks the most significant shift in fire's relationship with humanity since its initial domestication. For the first time in hundreds of thousands of years, we had major alternative to combustion for basic needs. Fire began transitioning from necessity to choice. Fire's role shifted from survival necessity to controlled utility. Throughout most of human history, fire was essential for survival. Without it, we'd have frozen in winter, eaten only raw food, lacked light after sunset, and remained vulnerable to predators. Fire knowledge was literally life or death important. This began changing with industrialization and modern technology. Central heating, electric lights, gas stoves, and processed foods reduced dependence on direct fire management. Today, millions of people rarely or never interact directly with fire. They might light birthday candles or occasional campfires, but fire isn't central to daily life. This represents a profound shift. We've outsourced fire management to power plants, refineries, and industrial processes. Fire still powers civilization, combustion engines, power generation, manufacturing. But it's hidden, controlled by specialists, removed from everyday experience. This distance from fire has costs and benefits, where safer house fires and burn injuries have decreased. But we've lost deep literacy with fire, skills, and knowledge that defined human competence for millennia. Most modern people couldn't reliably start fire without matches or lighters, couldn't maintain optimal cooking, fire, couldn't read fire behavior in landscapes. Fire's demotion from necessity to convenience represents major cultural transformation. Some survival skills, experts teach traditional fire-making methods. In response to growing distance from fire skills, some educators teach traditional fire-making as survival skill and cultural knowledge. Students learn bow drills, hand drills, flint and steel techniques, and fire by friction methods. These skills require practice, patience, and understanding of materials and technique. Successfully creating fire without modern tools provides deep satisfaction, connecting practitioners to ancestors who developed these methods. Survival schools emphasize fire making because it remains crucial wilderness skill. Fire provides warmth, water purification, signaling, and psychological comfort in emergency situations. The teaching also conveys respect for difficulty our ancestors faced. What seems simple, create fire, becomes challenging labor when stripped of modern conveniences. Students gain appreciation for matches, lighters, and other fire tools we take for granted. Learning traditional methods isn't just about emergency preparedness. It's about maintaining connection to human heritage, preserving knowledge that shouldn't be lost despite modern technology. These skills connect us to the long human relationship with fire, making explicit what was once universal knowledge. In learning to create fire from scratch, we touch something ancient and fundamental about human identity. Fire remains essential for many industrial processes. While personal fire use has declined, industrial combustion remains absolutely central to modern economy. Steel production requires blast furnaces, burning coke at extreme temperatures. Cement manufacturing depends on kilns, heating limestone. Petroleum refineries use fire for distillation and cracking processes. Chemical plants employ combustion in numerous processes. Waste treatment facilities incinerate materials. Power plants burn coal, gas, or biomass to generate electricity. Glass production, ceramics manufacturing, food processing, and countless other industries rely on controlled combustion. Modern civilization literally couldn't function without industrial fire. The scale is staggering. Single industrial furnaces burn more fuel in hours than thousands of home fireplaces burn in years. This hidden fire infrastructure, these massive industrial flames, power the economy and lifestyle most people experience. So while individuals interact less with fire directly, our collective dependence on combustion hasn't decreased. It's merely been centralized and hidden. The fire that once burned in every hearth now burns in specialized facilities, concentrated, efficient, and removed from public view, but absolutely essential to modern life. Cremation offers fire-based funeral practice. Humans dispose of dead through various methods, but cremation uses fire explicitly. Bodies exposed to extreme heat, typically 800 to 1000 degrees Celsius, for several hours, reduced to bone fragments and ash. These cremains can be kept, scattered, or buried according to family wishes. Cremation has ancient roots in multiple cultures, with ritual significance beyond practical disposal. Hindu tradition views cremation as releasing the soul, with elaborate ceremonies accompanying the practice. Buddhist cremation often follows specific rituals. In Western countries, cremation has grown more popular, viewed as simpler and less expensive than burial, while offering flexibility in memorialization. The process is very practical. Modern crematoriums use gas-fired furnaces with pollution controls, but carries psychological weight. Fire consumes the body, reducing physical form to elements, completing the transformation from living person to memory. This use of fire is deeply symbolic, employing combustion's most complete, transformative power. Fire that warmed us in life also receives us in death, completing the circle. For cultures and individuals choosing cremation, fire plays final role. Its ancient power invoked for last transition. Olympic cauldrons burn throughout the games as living symbol. When the Olympic flame lights the cauldron at opening ceremonies, that fire burns continuously until closing ceremonies weeks later. This constant flame, visible at the venue, serves as living symbol of the games in progress, representing tradition, competition, and international gathering. The cauldron must be designed to burn reliably regardless of weather, protected from rain and wind while remaining visible. Previous host cities have created spectacular cauldrons, tall towers, floating platforms, innovative designs that became architectural landmarks. The continuous flame demands constant fuel supply and monitoring, making it a significant logistical undertaking. Yet, the symbolism justifies effort. Athletes and visitors see the flame burning day and night, steady reminder of the event's significance. When it finally extinguishes at closing ceremonies, it marks definitive end, the festival's conclusion. This ritual use of fire, keeping flame alive throughout the games, connects to ancient practices of maintaining sacred fires. The Olympic flame serves no practical purpose. Its value is entirely symbolic, demonstrating fire's continued power as symbol, even in an era when it's no longer necessity. Fire-breathing performers command flame through careful technique. Fire breathers create spectacular displays by expelling fine mist of flammable liquid past open flame, creating large fireballs. The technique requires careful training. The performer holds fuel in their mouth without swallowing, positions torch precisely, and forcefully blows a fine spray that ignites dramatically, but burns completely before reaching the performer. Done wrong, it's extremely dangerous, with risks of severe burns to face and lungs if fuel is inhaled or technique fails. Professional fire breathers practice extensively with safety protocols, understand their fuel's properties, and maintain equipment carefully. The performance is thrilling, precisely because audience recognizes the danger. Controlling fire in such intimate, dramatic way demonstrates ultimate mastery, commanding flame's power through skill and courage. Fire breathing appears in various cultural traditions and has become popular performance art. It represents extreme example of fire as spectacle, using combustion's visual drama for entertainment. The performer's relationship with fire transcends normal interaction, achieving something that seems to defy safety and common sense. Yet, through knowledge and technique, they make it repeatable and relatively safe, turning fire into tool for creating wonder. Flamethrowing devices project burning fuel as weapons or tools. Flamethrowers project streams of burning fuel, creating weapons of terrible effectiveness or useful tools for controlled burning. Military versions have fortunately become rare, recognized as unnecessarily cruel weapons. But commercial versions designed for agricultural burning, clearing brush, or igniting prescribed fires remain common. These project flame accurately over distance, allowing operators to ignite specific areas from safe positions. The technology is simple: pressurized fuel forced through nozzle past ignition source, but the effect is dramatic. Watching flamethrower in action demonstrates fire's power and humanity's ability to project and direct combustion. The tool makes fire mobile and directed in ways impossible with other methods. For vegetation management, they allow precise ignition patterns. The device represents ultimate control over fire, no longer waiting for flame to spread but actively directing where combustion begins. Flamethrowers show fire transformed into beam or stream, turned into projectile, made to reach across distance. This extension of fire's reach demonstrates human ingenuity in developing technologies that amplify and control combustion's effects. Welding uses extreme heat to fuse metals permanently. Welding achieves temperatures high enough to melt metal, allowing pieces to be fused into unified structures. Various welding methods exist. Arc welding uses electrical discharge to generate heat. Gas welding burns acetylene or similar fuels. Thermite welding uses chemical reactions, producing molten iron. All involve extreme temperatures, controlled precisely through technique and equipment. The welder must understand materials, heat control, and proper technique to create strong, clean joints. Modern civilization depends utterly on welding buildings. Vehicles, ships, pipelines, infrastructure, all rely on welded joints. Before welding, metal structures were bolted, riveted, or forged, limiting design possibilities. Welding allows complex shapes, lightweight structures, and joints stronger than the metal itself. The technique represents fire's application at extreme level. Using heat so intense, it makes solid metal flow. Watching molten metal glow and combine, seeing solid material become liquid, then re-solidify as unified piece, demonstrates transformation that only extreme heat enables. Welding is fire as industrial tool, combustion, or electrical discharge, creating temperatures that reshape physical reality. Kilns have evolved from simple pits to sophisticated furnaces. The first pottery was likely fired in open pits, covered with fuel and earth. Over time, kilns evolved into sophisticated structures, optimizing heat control and fuel efficiency. Ancient kilns ranged from simple updraft designs to complex multi-chamber systems. Modern electric kilns offer precise temperature control, programmable heating cycles, and even atmosphere regulation. Gas kilns provide traditional firing, while maintaining consistency. Wood-fired kilns, still used by some traditional potters and artists, create unique effects as ash from burning wood glazes the pottery naturally. Each kiln type offers advantages: electric for precision, gas for economy and power, wood for aesthetic effects. The evolution shows humanity's increasing mastery of controlled heat environments, from simple holes in ground to sophisticated furnaces, maintaining specific temperatures for hours. Regardless of sophistication, all kilns do one thing: contain fire and heat at levels high enough to transform materials. Modern kilns might use electricity or gas rather than wood, but they still serve fire's essential function, creating controlled high-heat environments where transformation occurs. The kiln is architecture for fire, a structure whose sole purpose is managing combustion and heat. Ovens evolved from open fires to precise cooking environments. The first human cooking was over open flames, direct and simple but difficult to control. Ovens represented major advancement in closed spaces where heat could be contained and controlled, creating more consistent cooking conditions. Early ovens were often clay or stone structures heated by building fire inside, then removing coals before cooking. Wood-fired ovens reached high temperatures perfect for bread and pizza, creating textures impossible with other methods. Coal and later gas ovens brought convenience, maintaining steady heat without constant fuel addition. Electric ovens eliminated combustion from home cooking entirely, offering precise temperature control. Modern ovens include convection features, self-cleaning cycles, and digital controls. Despite sophistication, the principle remains unchanged: to create controlled heat environment for cooking food. Ovens represent fire domesticated and specialized, combustion transformed from general-purpose tool to appliance designed specifically for one purpose. The evolution from open fire to modern oven mirrors humanity's journey with fire itself, from direct, demanding relationship, requiring constant attention, to controlled, convenient appliance, requiring only basic interaction, yet both achieve the same fundamental goal: using heat to transform food. Stoves brought cooking fire into controlled appliance form. Wood-burning cook stoves represented major improvement over open hearth cooking. Instead of tending open fires and juggling pots, cooks had flat surfaces that could support multiple vessels, oven compartments for baking, and relatively controllable heat through air dampers. These cast-iron stoves became kitchen centerpieces, providing heat and cooking capability while requiring skill to operate effectively. Coal stoves followed similar principles with different fuel. Gas stoves revolutionized cooking, with instantly controllable flame, precise heat adjustment, and no need for fuel storage or ash removal. Electric stoves eliminated visible flame entirely, but maintained cooktop and oven functionality. Despite different heat sources, all stoves serve the same purpose: providing controlled cooking heat in convenient form. Modern stoves are so reliable and easy that we forget cooking's fire origins. The blue flame of gas burner, or glowing element of electric stove, are distant descendants of open cooking fires, highly evolved, but fundamentally still applying heat to food. The stove represents one of fire's most successful domestications: transformation from open flame requiring constant attention to appliance that turns on reliably at a switch or dial. Broilers use direct heat from above, like inverted campfires. Broilers in ovens, position heating element or flame above food, cooking from top down with intense direct heat. This mimics cooking method where meat is suspended above fire, but inverted, the heat comes from above rather than below. Broiling creates specific effects: browning and caramelization on surfaces, crispy exteriors while maintaining moist interiors, excellent for melting cheese or finishing dishes. The method works because intense, radiant heat transfers quickly, cooking surfaces rapidly. Professional kitchens use salamander broilers, powerful overhead units for finishing dishes. Home oven broilers, whether gas flame or electric element, provide similar capability. The technique is primal in some ways: direct high heat applied to food, like thrusting meat near flames, but contained and controlled in appliance. Broiling reminds us that even in modern kitchens with sophisticated equipment, we're still using fire's heat, still applying intense thermal energy to transform food. The broiler is fire overhead, heating element positioned to radiate downward, recalling campfire methods while offering precision and safety impossible with open flames. Slow cookers and pressure cookers use indirect heat for efficiency. Not all fire-based cooking uses high, direct heat. Slow cookers maintain low temperatures for hours, breaking down tough cuts and developing flavors through extended gentle heating. Pressure cookers contain heat and pressure, cooking food faster than traditional methods. Both rely on electric heating elements or stovetop burners, fire or electricity, creating heat that these appliances manage specifically. They represent sophisticated fire control, using combustion-generated energy, but mediating it through technology to achieve specific cooking outcomes. These devices show that effective cooking isn't just about high heat, but about right heat applied properly. The slow cooker's patient warmth and pressure cooker's intensified environment both achieve results impossible over open flames. They demonstrate fire's evolution. In cooking from our only option to energy source, we manipulate through various technologies for specific purposes. Modern cooking is still fundamentally about applying heat to food, about using fire's descendant energy, but the sophistication of control has increased dramatically. The grandmother's open fire cooking and the pressure cooker both use heat to transform food. The latter just does so with remarkable efficiency and precision. Smokers use low heat and smoke for preservation and flavor. Smoking food combines low-temperature cooking with smoke exposure, creating distinctive flavors while preserving meat. Traditional smoking occurred in smokehouses where meat hung near smoldering fires, exposed to smoke for days or weeks. Modern smokers range from simple charcoal units to sophisticated electric or gas-powered systems, but principle remains unchanged. Low heat and wood smoke transform and preserve food. Different woods create different flavors: hickory, mesquite, apple, cherry, each imparting unique taste. The smoking process requires patience and skill, maintaining proper temperature, managing airflow, choosing appropriate wood. Cold smoking preserves without cooking. Hot smoking cooks while flavoring. Smoking represents one of humanity's oldest preservation techniques, using fire not primarily for heat, but for its byproducts, smoke and gentle warmth. Before refrigeration, smoking kept meat edible for months, essential for surviving winter or making portable provisions. Today, smoking is mostly about flavor rather than preservation. But the technique connects us to ancestors who developed and refined these methods over thousands of years. Every bite of smoked barbecue or smoked fish carries echoes of fires tended by people long forgotten, their knowledge preserved in continued practice of this ancient art. Barbecue traditions vary globally, but share fire as foundation. Barbecue means different things in different cultures. American barbecue emphasizes slow-smoked meat. Korean barbecue features grilling at table. Argentine asado celebrates whole animals over wood fires. Australian barbie is straightforward grilling. Despite variations, all share fire's heat applied to meat. The specifics differ: types of meat, seasoning, cooking methods, social contexts. But fire remains central. Barbecue represents one of the most widespread cultural connections to fire, maintaining direct relationship between flame and food. Even those who rarely interact with fire otherwise might barbecue, managing coals and flames, learning heat control through practice. Barbecue social events bring people together around fire, continuing ancient tradition of gathering for cooking and eating. The smell of charcoal or wood smoke, the sight of flames licking meat, the care required to manage heat, These engage us with fire directly. Barbecue culture worldwide represents collective commitment to fire-cooked food, refusal to abandon completely the ancient partnership between flame and feast. In an age when most cooking happens on stoves or in ovens, barbecue preserves direct fire cooking, keeping skills and traditions alive. Charcoal grilling offers distinct flavor from wood combustion products. Gas grills are convenient, but charcoal advocates insist nothing matches the flavor charcoal imparts. This flavor comes from smoke created when meat drippings fall onto hot coals, vaporize, and rise back over food. The charcoal itself, being nearly pure carbon, produces minimal smoke, but it reaches very high temperatures, creating ideal conditions for searing. Wood chunks added to coals increase smoke, enhancing flavor. The science shows that smoke contains hundreds of compounds, phenols, carbonyls, furans that adhere to food surfaces, creating complex flavors. Gas grills can't replicate this chemistry exactly, though some designs attempt smoke generation. For enthusiasts, this flavor difference justifies charcoal's inconvenience. Longer start times, temperature control challenges, ash cleanup. Charcoal grilling maintains traditional fire relationship, requiring skill to build proper coal beds, manage heat through damper control and coal arrangement, and time cooking appropriately. It's more demanding than gas grilling, but for many, this engagement is part of the appeal. Working with charcoal means working with fire more directly, accepting its demands and variability as part of the experience. The resulting flavor becomes not just chemical compounds, but taste of that effort and connection. Pizza ovens reach temperatures impossible in home ovens. Traditional pizza ovens burn wood, reaching temperatures of 800 to 900 degrees Fahrenheit or higher. At these temperatures, pizza cooks in just minutes, crust developing leopard-spotting char, while remaining soft, cheese melting but not overcooking. The high heat, and often dome-shaped interior, creates specific heat environment impossible to replicate in home ovens that typically max around 500 to 550 degrees. This temperature difference explains why home pizzas rarely match pizzeria quality. The physics simply differ. Some enthusiasts build wood-fired ovens at home or purchase portable versions, seeking that authentic, high-heat cooking. Others use workarounds, pizza stones, broiler techniques, modified appliances attempting to approximate wood oven conditions. The wood-fired pizza oven represents specialized fire technology, designed specifically to achieve temperatures for one purpose. It shows how controlling fire at extreme temperatures enables specific culinary results. The Neapolitan pizza tradition centers on wood-fired ovens, with exact construction specifications and techniques passed through generations. These ovens aren't just cooking equipment, but cultural artifacts, repositories of accumulated knowledge about how fire and flour transform into one of humanity's most beloved foods. Tandoor ovens use retained heat in clay structures. In South Asian cuisine, tandoor ovens, cylindrical clay structures heated to extreme temperatures, cook breads and meats with distinctive char and smokiness. The tandoor is heated by burning wood or charcoal inside until the clay walls absorb tremendous heat. Then the fuel is reduced, and cooking happens in the residual heat radiating from those walls, with food stuck directly onto the hot interior or skewered and suspended inside. Naan bread achieves its characteristic charred bubbles and soft interior from this cooking method. Tandoori chicken develops complex flavors from intense heat and slight smoke. The tandoor demonstrates sophisticated fire management, building fire to heat thermal mass, then using stored heat for cooking, creating intense, radiant heat environment different from direct flame cooking or oven baking. This technology developed over centuries, optimized for specific culinary traditions, Modern restaurants often use gas-fired tandoors, maintaining proper temperatures more conveniently, but traditional wood or charcoal methods remain preferred by purists. The tandoor shows that cooking with fire involves not just flame, but understanding heat transfer, thermal mass, and how to create specific temperature environments. Fire knowledge extends beyond mere combustion to sophisticated thermal engineering. Cast iron cookware has been used for centuries over fire. Before non-stick coatings and modern materials, cast iron reigned in kitchens. Heavy, durable, and able to withstand extreme temperatures, cast iron skillets, pots, and Dutch ovens worked equally well over open fires, on wood stoves, or in ovens. The material's heat retention properties made it ideal for fire cooking. It maintains steady temperature despite fluctuations in heat source. A properly seasoned cast iron skillet develops non-stick surface through layers of polymerized oil, improving with use. Cast iron withstands abuse that would destroy modern cookware: direct flame contact, extreme temperature changes, metal utensils. This durability meant generations used the same pots, developing patina and character over decades. Today, cast iron has experienced revival, valued for its versatility and traditional qualities. Using cast iron connects cooks to generations past, when these heavy black pots were kitchen essentials. The weight, the care required for seasoning, the way heat distributes evenly, all these qualities made cast iron perfect partner for fire cooking. Modern cookware offers advantages, but cast iron maintains loyal following among those who appreciate its fire heritage and enduring utility. Fire festivals celebrate light in darkness across cultures. Throughout the year, various cultures celebrate festivals centered on fire. Diwali, the Hindu festival of lights, features oil lamps illuminating homes and streets. Hanukkah remembers miraculous oil, keeping temple flames burning. Christmas traditions include Yule logs and candles marking winter light. Up Heli Ayr in Scotland features torch processions and burning Viking ships. Las Fallas in Spain culminates in burning enormous artistic sculptures. Guy Fawkes Night in England involves bonfires and fireworks. Midsummer celebrations across Europe feature bonfires marking the solstice. These festivals, despite different cultural contexts, share common theme: fire as celebration, light conquering darkness, flame as communal experience. They continue ancient traditions, when fire was humanity's only significant light source, when flames held both practical and symbolic importance. Even in electric age, these fire festivals persist, suggesting deep human connection to flame transcends practicality. Fire's ability to gather communities, create spectacle, and mark significant moments remains powerful. These celebrations honor fire not just as tool but as symbol, recognizing its role in human story and continuing rituals that connect us to ancestors who relied on flame for survival. Diwali lamps illuminate millions of homes in celebration. During Diwali, Hindus, Jains, Sikhs, and others light small oil lamps called diyas, placing them on windowsills, doorways, and throughout homes. The effect, multiplied across millions of households, creates waves of light across India and worldwide Indian communities. The festival celebrates light over darkness, knowledge over ignorance, good over evil. Traditional diyas are simple clay cups with cotton wicks soaking in oil, creating small flames that flicker and glow throughout celebration nights. Modern celebrations often include electric lights, but traditional oil lamps maintain special significance. Lighting diyas is spiritual practice, each flame representing prayer or devotion. The collective effect of countless small flames creates beauty and meaning beyond individual lamps. Diwali shows fire's enduring spiritual significance. flames as offerings, as symbols, as markers of sacred time. The festival's light transforms ordinary spaces into celebration, making visible the invisible devotion of millions. In Diwali's flames, we see fire's power to unite, to signify, to transform the everyday into the sacred, through simple act of lighting wicks and maintaining flame. Advent candles mark the approach of Christmas week by week. In Christian tradition, Advent wreaths hold 4 or 5 candles, lit progressively through the 4 weeks before Christmas. Each Sunday, another candle is lit, increasing light as Christmas approaches. The practice symbolizes anticipation, the growing light representing Christ's coming. Families gather weekly around Advent wreaths, lighting candles with prayers and readings. The ritual creates structure and meaning. In the weeks before Christmas, each flame marking progression through waiting. The final candle often lights on Christmas itself, completing the sequence. This use of fire creates tangible countdown, visible measure of time passing and holiday approaching. Watching flames grow from 1 to 2 to 3 to 4 candles provides concrete representation of abstract concept anticipation made visible. Children especially appreciate this physical manifestation of counting down to celebration. Advent candles show fire as timer, as marker of progression, flames measuring not just space or heat but time itself. The tradition continues because flame provides something electric lights cannot sense of significance, ritual action, and ancient symbolism bound in simple practice of lighting successive candles. Hanukkah menorah commemorates ancient oil miracle through flame. The Jewish festival of Hanukkah celebrates a miracle where 1 day's worth of oil kept the temple menorah burning for 8 days. Modern Hanukkah observance includes lighting a 9-branched menorah, adding 1 candle each night for 8 nights, with the 9th candle used to light the others. Families gather nightly for the lighting ceremony, saying blessings and singing songs as flames grow from 1 to 8 over the festival's progression. The menorah's flames are meant to publicize the miracle, so tradition places them in windows or doorways where others can see. Children watch flames burn down, receiving gifts and playing games while light fills the home. Like Advent candles, the menorah creates visual progression through celebration, each night adding light. The specific historical connection to miraculous oil burning makes flame particularly appropriate symbol. Without fire, Hanukkah would lose essential element. The flames themselves are the point, representing the miracle being remembered. Modern electric menorahs exist but lack the living quality of actual flames, the connection to ancient oil lamps that inspired the holiday. Bonfires mark seasonal transitions in many traditions. Solstice celebrations across cultures feature bonfires, marking summer's peak or winter's depth. Midsummer fires in Scandinavia, Europe, and elsewhere celebrate longest day, flames leaping high as communities gather. Winter solstice fires mark darkest time, promising sun's return. These bonfires serve both practical and symbolic purposes, historically helping drive away wild animals, lighting festivities, and providing warmth for outdoor gatherings. Symbolically, they represent human ability to create light and heat in darkness, defiance of night and cold, celebration of fire's power. The scale of celebration bonfires matters. Larger fires create more impressive spectacle, draw bigger crowds, and demonstrate communal effort in gathering fuel and building fire. Some traditions include throwing offerings into flames or leaping over fires for luck. These practices connect modern celebrations to ancient fire rituals, continuing traditions thousands of years old. The solstice bonfire is fire as event, flame elevated beyond utility into communal celebration, marking time's passage and humanity's place in natural cycles. Burning Man Festival centers on symbolic fire in the desert. Burning Man, the annual gathering in Nevada's Black Rock Desert, culminates in burning a large wooden effigy, the man. Tens of thousands gather to watch this massive structure burn, flames visible for miles across the dark desert. The event's name explicitly references fire, making combustion central to the festival's identity. Participants create elaborate art installations, many of which burn during the week-long event. Fire dances, flame effects, and pyrotechnic displays fill the nights. The final burning of the man represents various things to different participants: release, renewal, transformation, spectacle, or simply impressive display of controlled conflagration. The event shows fire's continued power as focus for community gathering, as symbol of transformation, and as spectacle that awes despite living in technological age. Burning Man creates temporary city in harsh desert, and fire becomes its spiritual center, the literal burning that gives the gathering its identity. It demonstrates that humans still gravitate toward large communal fires, still find meaning and excitement in watching flames consume significant structures. Yule logs originally burned through entire winter celebrations. The Yule log tradition originated in European winter celebrations where large logs were selected, brought home with ceremony, and lit in hearth to burn throughout winter festivities. The logs burning symbolized warmth and light through darkest season, and keeping it burning was considered good luck. Pieces of the log might be saved to kindle next year's Yule fire, creating continuity across years. This tradition required massive fireplaces that could accommodate logs several feet long, and the logs needed to burn slowly, continuing throughout the multi-day celebrations. The practice largely faded as fireplaces shrank and central heating arrived, but the symbolism persisted. The chocolate Yule log dessert represents culinary memory of the tradition. Some still burn Yule logs at winter holidays, recreating ancient practice. The tradition shows fire's role in winter survival and celebration, how flames' warmth and light took on symbolic meaning beyond mere heating. The Yule log was fire, as companion through darkness, practical warmth elevated to ritual significance, combustion marking sacred season. Eternal flames at memorials keep memory alive through fire. Many memorial sites feature eternal flames that burn continuously, commemorating events or individuals. President Kennedy's grave at Arlington National Cemetery, the tomb of the unknown soldier in various countries, Holocaust memorials, and war memorials worldwide maintain perpetual flames. These fires serve no practical purpose, their value is entirely symbolic. The unending flame represents memory that must not fade, vigilance that must not cease, significance that transcends normal time. Maintaining eternal flames requires constant attention fuel systems, weather protection, monitoring, and quick response if flame extinguishes. This effort demonstrates commitment to remembrance. The flame's vulnerability, it can go out, makes its continuation meaningful. When people tend eternal flames, they perform ritual act of remembrance, making abstract memory concrete through fire maintenance. These flames connect, present to past through continuous combustion, literal link, stretching across time. Fire that burned yesterday, burns today, will burn tomorrow, each moment's flame feeding the next in unbroken chain. For visitors, seeing the eternal flame burning provides comfort, assurance that memory persists, symbolized by fire that refuses to die. Fire juggling combines skill and spectacle with controlled danger. Fire jugglers toss flaming torches, clubs, or other objects in complex patterns, creating trails of light through darkness. The skill required is considerable. Juggling itself demands coordination and practice. Adding fire increases difficulty and danger significantly. Performers must manage heat, avoid burning themselves, maintain juggling patterns, and often perform to music or as part of larger shows. The effect is mesmerizing. Flame arcs, drawing temporary patterns against night, patterns that exist only in moment of performance and in observers' memories. Fire juggling represents ultimate domestication of flame taken from hearth and campfire, reduced to torch-sized portions, tossed through air in entertainment. Yet it retains fire's essential danger and power, making performances thrilling. The audience watches with mix of appreciation for skill and awareness of risk. Fire juggling shows fire as pure performance element, combustion serving no purpose but aesthetic impact and demonstration of human ability to control what normally burns beyond our grasp. It's fire made portable, airborne, and beautiful through skill and daring. Sacred fires have been maintained for centuries. In some temples, various religious traditions maintain sacred fires kept burning continuously, sometimes for centuries. Zoroastrian fire temples preserve flames considered pure and sacred, with priests tending them constantly. Some Hindu temples maintain eternal flames representing divine presence. These fires carry deep religious significance. They're not mere symbols but holy objects themselves, treated with reverence and protected carefully. The continuity matters enormously. A fire that has burned for centuries represents unbroken tradition, connection to ancient origins, spiritual continuity made physical through maintained flame. Priests or monks who tend these fires follow specific rituals and protocols, their primary duty ensuring flame never extinguishes. If extinction occurs, it's considered catastrophe, requiring purification and rededication. These sacred fires show fire's elevation to divine status, combustion sanctified beyond any practical purpose. The flames become conduits to the sacred, focal points for devotion, living links to divine realm. Their heat and light are not merely physical but spiritual, fire serving as intermediary between material and transcendent worlds. Incense burning creates aromatic smoke for spiritual purposes. Incense burning appears in religious practices worldwide. Buddhist temples, Catholic churches, Hindu pujas, and countless other contexts. The smoke rising from smoldering incense carries prayers upward symbolically, purifies sacred spaces, and creates sensory experience associated with worship. Different materials produce different aromas: sandalwood, frankincense, myrrh, sage, cedar, copal, each with traditional significance. The burning is incomplete combustion, producing smoke rather than flame, using fire's heat to release aromatic compounds without consuming material completely. Incense sensors and burners represent specialized fire technology designed to maintain proper smoldering temperature while containing ash and embers safely. The practice connects smell with devotion, creating olfactory memories of sacred experiences. When practitioners smell particular incense later, memories of worship and reverence return. Incense burning demonstrates fire's versatility, not always about maximum heat or bright flame. Sometimes fire's purpose is creating smoke, releasing scent, producing sensory effect that enhances spiritual experience. It's fire as perfume generator, combustion, controlled precisely for specific aromatic outcome. Sage smudging uses smoke in cleansing ceremonies. Many indigenous American traditions use sage smoke in spiritual cleansing ceremonies called smudging. Dried sage burns with distinctive aroma, and participants waft smoke over themselves, others, or spaces to purify and bless. The practice represents spiritual technology using fire and smoke as agents of cleansing, washing away negative energy or influences. Smudging has gained popularity beyond its indigenous origins, though this adoption raises questions about cultural appropriation and respect for sacred practices. Regardless, The practice demonstrates fire's role in spiritual cleansing, smoke as purifying agent. The ritual typically involves lighting sage bundle, letting it flame briefly, then blowing it out so it smolders and smokes. The smoke is directed intentionally with feathers or hands, accompanying prayers or intentions. This use of incomplete combustion for spiritual purpose shows fire's flexibility. It's not the flame that matters here, but the smoke, the aromatic compounds released by partial burning. Fire serves purification function, combustion transformed into cleansing ritual, passed through generations. Firewalk ceremonies challenge participants to walk across hot coals. Firewalking appears in various cultural and spiritual traditions worldwide. Participants walk barefoot across beds of glowing coals, reaching hundreds of degrees, typically emerging unburned. The practice seems impossible. How can feet contact such heat without injury? Physics provides answers involving brief contact time, low thermal conductivity of ash and air pockets in coal beds, and the Leidenfrost effect, where moisture vaporization briefly insulates. But scientific explanation doesn't diminish the experience's impact. For participants, firewalking represents conquering fear, demonstrating faith, or achieving altered state through ritual. The psychological component is the significant belief that one can traverse fire successfully seems crucial to actually doing so without injury. Modern motivational events sometimes include firewalking as team building or confidence exercise, divorced from original spiritual contexts. This commercialization is controversial, but it demonstrates fire's continued power as transformative challenge. Walking across fire requires confronting primal fear, trusting in technique or faith, and experiencing fire's heat directly. Those who complete firewalks report profound psychological impact, feeling empowered and transformed. Fire becomes teacher, testing ground, and ultimately conquered fear. Candle meditation uses flame as focal point for contemplation. In various meditation traditions, candles serve as focal points for concentration. Practitioners gaze at flame, using its movement and light as anchor for attention. The flickering draws the eye naturally, providing something to focus on without being distracting. As mind wanders, return to watching flame. The practice, called tritaka in some yoga traditions, aims to develop concentration while calming mind. There's something inherently meditative about watching fire, the constant movement without repetition, the play of light and shadow, the gentle warmth, if close enough. Flame watching can induce mild trance states, quieting mental chatter. The candle becomes partner in meditation, its steady burning matching the steadiness practitioners cultivate internally. This use of fire for mental training shows combustion serving psychological purposes, flame as tool for consciousness work. The meditation doesn't require elaborate theology or complex techniques. Simply watching flame attentively can create meditative state. Fire's ancient role in human experience perhaps makes it naturally effective for this purpose, tapping into deep associations between flame and contemplation that formed around countless ancestral fires. Fire's warmth creates comfort that transcends mere temperature. There's something about fire's warmth that feels different from other heat sources. Electric heaters warm efficiently, but they lack fire's quality. Perhaps it's the radiant heat's gentle intensity, warming skin directly without heating air as much. Maybe its visual component, seeing flames, while feeling heat creates multisensory experience. Or perhaps it's psychological, evolutionary memory of fire as safety and comfort. People sit closer to fires than they do to heaters, drawn by something beyond temperature. They arrange furniture facing fireplaces, orient spaces around hearths. In restaurants, fireplace tables are most requested. This suggests fire's warmth carries meaning beyond physics, that radiant heat from flame affects us differently than convection from vents. The slight variation in fire's heat, the gentle fluctuations as flames rise and fall, may be more pleasant than steady mechanical heating. Fire breathes, rises and falls in natural rhythm that artificial heat lacks. Its warmth feels alive, connected to the dancing flames that generate it. This living quality of fire's heat may explain why people still value fireplaces despite having more efficient heating, why fire's warmth remains special in ways thermostats cannot replicate. The sound of fire is deeply soothing to many people. Crackling campfires, snapping logs, the gentle roar of sustained flames. The fire's sounds are used in sleep apps, relaxation recordings, and ambient soundtracks worldwide. Why do we find these sounds soothing? Perhaps because our ancestors spent countless nights around fires, making these sounds deeply familiar at subconscious level. The crackle signals warmth, safety, community. Or maybe it's the randomness. Fire sounds are unpredictable in timing and character, providing acoustic complexity without demanding attention. They mask other sounds without being intrusive. The slight variation keeps sound interesting without being stimulating, walking perfect line between boring and engaging. Unlike music or speech that demand processing, fire's sounds wash over us, requiring nothing. Studies suggest natural sounds like fire, rain, or waves activate parts of the brain associated with rest and external focus, shifting attention outward in a relaxing way. Listening to fire allows mind to wander while anchored by sound, creating ideal conditions for relaxation or sleep. That fire recordings are popular despite modern separation from actual flames suggests deep human resonance with these sounds, acoustic signature of comfort coded into our species over hundreds of thousands of years. Watching flames can reduce stress and lower blood pressure. Research indicates that watching flames has measurable physiological effects. Heart rate decreases, blood pressure lowers, and stress hormones reduce during fire watching. This may connect to evolutionary history. Successful fire management meant survival, so calm attention to flame was adaptive. Or perhaps flame watching induces mild meditative state, producing relaxation effects. The visual complexity of flame offers endless variation without overwhelming, providing stimulation that's engaging but not demanding. Flame watching doesn't require decisions or responses, allowing passive observation that's fundamentally restful. Some researchers compare it to fractals. Flame's structure contains similar patterns at different scales, which humans find inherently pleasing. Colors matter too. Warm oranges and yellows may trigger positive associations with warmth and safety. Whatever the mechanisms, the effect is real. People sitting before fires report feeling calmer, more relaxed, more present. Stress seems to dissolve in flame's glow. This may explain fire's enduring appeal despite losing practical necessity. Even when we don't need fire for warmth or cooking, we benefit from its presence, psychologically. Its flames providing balm for modern stress that our ancestors never experienced, but our nervous systems appreciate nonetheless. Fire connects us to history and our ancestors in tangible ways. When you light a fire, you perform action your ancestors did countless times. The motions arranging kindling, striking match, watching flame catch and spread connect you across time to every human who ever built fire. The skill might use modern tools, but the fundamental act remains unchanged. This continuity is profound. Fire represents one of humanity's oldest technologies, so old it predates our species. Every culture everywhere has fire traditions, stories, skills passed through generations. When you sit before a fire, You share experience with ancestors from every era, every continent. They knew this warmth, watched these colors, felt this comfort. Fire is universal human experience, common thread weaving through all our histories. In disconnected modern world, this connection to the past through fire can feel grounding, reminding us we're part of continuous human story. The fire burning in your fireplace or campfire is the same element that warmed your ancestors, cooked their food, protected them from darkness and predators. Through fire, we touch history directly, maintaining living link to human past that few other activities provide. And so, dear listener, we have traveled together through fire's many forms, from the sun's nuclear furnace to the candle's gentle glow, from ancient hearths that built civilization to modern flames that continue shaping our world. We have seen fire as survival necessity and spiritual symbol, as destructive force and creative power, as ancient companion and ever-present mystery. Fire transforms. It changes wood to ash, clay to pottery, ore to metal, night to day. But perhaps fire's greatest transformation is how it changed us, how mastering flame made us human in ways that transcend biology. Around fire, we became storytellers, artists, cooks, and dreamers. By fire's light, we built cultures, civilizations, and meaning itself. As you settle now into rest, imagine yourself beside a perfect fire. See the flames dancing gently, casting warm light into comfortable darkness. Hear the soft crackling, the occasional pop of wood, the peaceful roar of steady burning. Feel the warmth on your face, gentle and soothing, wrapping around you like an embrace. Smell the wood smoke, that ancient aroma that speaks to something deep within, carrying comfort and safety in its familiar scent. Watch the flames shift and flow, never the same from one moment to the next, endlessly fascinating yet infinitely calming. See the coals glowing beneath, orange and red and white, holding heat in their heart. Notice how the fire breathes, rising and falling in natural rhythm, patient and eternal, exactly as it should be. Let fire's warmth sink into your muscles, releasing tension you didn't know you held. Let its light soften the edges of thought, making space for rest. Let its ancient presence remind you that you are safe, you are warm, you are home. The fire will burn through the night, steady and faithful, asking nothing of you. It will keep watch while you sleep, as fire has done for countless generations before. You need only rest now, letting go, trusting in the warmth that surrounds you, the light that remains even as your eyes grow heavy. Breathe in the peace of flame-lit darkness. Breathe out the weight of the waking world. Let yourself drift on fire's gentle currents, floating towards sleep as naturally as smoke rises, as surely as flames dance. The fire burns on, and you are safe, and all is well. Close your eyes now, dear friend, and let sleep find you in fire's warm embrace. Let your last waking thoughts dissolve like sparks into the night, carried upward on gentle heat, fading softly into rest. Good night. Asterisk. The fire crackles softly in the darkness, its warmth and light to a faithful companion through the night, as it has always been, as it will always be, burning gently while you sleep. Asterisk.